Sound begins not as something we hear, but as something that moves, a subtle disturbance in matter, a ripple of energy that travels through a medium by making particles dance in place. And to understand it, we must first imagine a world without ears, without interpretation, without language, where sound is simply vibration, mechanical energy transferring from one molecule to the next in a chain reaction of motion. When an object moves, whether it is a plucked guitar string, a clapping hand, or the sudden crack of thunder, it pushes against the air surrounding it, compressing the molecules in front of it into a tighter space, creating a region of higher pressure known as compression, and as those molecules push forward, they spread apart behind them, forming a region of lower pressure called rarefaction. And this alternating pattern of compression and rarefaction travels outward in a longitudinal wave, meaning the motion of the particles is parallel to the direction the wave moves. Unlike ocean waves that appear to roll across the surface while water mostly moves up and down, in sound waves, the air itself does not travel across the room from speaker to listener. Rather, the energy passes through stationary molecules like a domino effect, each particle nudging the next and returning to its original position, and this subtle choreography defines the invisible architecture of acoustics. The frequency of these oscillations, measured in hertz, determines pitch, with higher frequencies producing higher tones and lower frequencies producing deeper sounds, while amplitude, the height of the pressure variation, determines loudness, though loudness is also shaped by the sensitivity of the human ear and the logarithmic nature of decibel measurement. Wavelength, the physical distance between compressions, shrinks as frequency rises, meaning high-pitched sounds have shorter wavelengths, while bass tones stretch farther between peaks. Yet the most essential truth about sound is that it requires a medium, a collection of particles capable of interacting, because without matter, there is nothing to compress, nothing to rarefy, nothing to carry the wave forward. And this is why sound cannot travel through a vacuum, because in empty space, there are too few molecules to transmit that mechanical disturbance. This dependence on matter distinguishes sound from light, which is an electromagnetic wave capable of propagating through vacuum at the astonishing speed of approximately 300,000 kilometers per second, while sound in air at room temperature moves at roughly 343 meters per second, a difference so vast that we see lightning long before we hear thunder. And this disparity reveals something profound about the nature of waves. Some are mechanical and require a medium. Ears are electromagnetic and self-sustaining oscillations of electric and magnetic fields. When we speak, our vocal cords vibrate as air from the lungs passes through them, shaping pressure waves that travel through air and into another person's ear, where they strike the eardrum, causing it to vibrate in sympathy, transferring energy through tiny bones, known as the ossicles, and into the cochlea, where fluid motion bends microscopic hair cells that convert mechanical motion into electrical signals interrupted by the brain as sound, meaning what we perceive as a voice or music is ultimately a translation of pressure patterns into neural impulses, and thus sound is both a physical phenomenon and a perceptual experience. Beyond air, sound behaves differently in other materials, traveling faster in liquids and even faster in solids because particles are closer together and can transmit vibrations more efficiently, which is why placing your ear against a railway track allows you to hear a distant train before it becomes audible through air. And this property reveals how intimately sound is tied to density and elasticity, since the speed of sound in a medium depends on how quickly that medium can respond to compression and restore itself. Elasticity allows the medium to spring back after being compressed, while density determines how much inertia resists motion, and the balance between. And these properties defines acoustic velocity. Yet despite its invisibility, sound leaves measurable traces. Oscilloscopes visualize waveforms. Microphones convert pressure into electrical signals, and mathematical equations describe wave propagation with remarkable precision, including the wave equation that links spatial and temporal variations in pressure. Still, at its core, sound remains elegantly simple. It is organized vibration traveling through matter. In the earliest moments of the universe, before atoms formed, the cosmos itself carried pressure waves through its hot plasma, meaning sound, in some primordial sense, predates stars and galaxies. Though today in the near vacuum between celestial bodies, silence reigns because there is almost no medium to sustain mechanical waves. And so when we consider sound, we are really contemplating motion made audible, energy shaped into rhythm, the transformation of vibration into perception, a bridge between physics and consciousness. Every whisper, every explosion, every heartbeat is an arrangement of compressions and rarefactions, moving through matter, and though our ears interpret them emotionally, as music, as warning, as comfort, the universe itself simply follows physical laws, transferring energy molecule to molecule in a pattern that can be described, measured, predicted, yet still inspires awe. Sound is not an object, but an event, not a thing, but a process. Born the moment motion disturbs equilibrium and propagated through the cooperative motion of countless particles. And in that sense, the birth of a vibration is the birth of communication itself, because wherever matter exists and energy moves through it, there exists the potential for sound, waiting to be heard, measured, or simply allowed to fade back into stillness. Sound does not travel as a visible object, moving from one place to another, but as an organized transfer of energy that passes through matter by setting its particles into coordinated motion. And to truly understand this journey, we must imagine matter not as solid and still, but as a restless field of atoms and molecules constantly vibrating even at room temperature, each particle bonded to its neighbors by electromagnetic forces that allow them to push and pull against one another. And when a sound source such as a vibrating drumhead disturbs the air, it pushes the nearest air molecules closer together, creating a region of compression where pressure momentarily increases, and those compressed molecules, unable to remain crowded due to their mutual repulsion, push outward against adjacent molecules, transferring energy forward in a chain reaction that continues outward in all directions, forming a longitudinal wave in which the oscillations of particles occur parallel to the directio n of wave propagation. Yet the individual particles themselves travel only tiny distances around their equilibrium positions, oscillating back and forth rather than moving across the room, meaning that what truly travels is not matter but momentum and energy, passed from one particle to the next like a synchronized relay. In gases such as air, where molecules are relatively far apart compared to solids and liquids, sound travels at approximately 343 meters per second at room temperature, though this speed changes with temperature because warmer air contains faster moving molecules that can transmit compressions more rapidly, illustrating how thermal energy influences acoustic velocity. When we shift our attention to liquids, such as water, we find that sound travels significantly faster, roughly 1,480 meters per second. Roughly 1,480 meters per second, because water molecules are more closely packed and can transfer vibrational energy more efficiently. And in solids, the speed increases even further, often exceeding 5,000 meters per second in materials like steel, where tightly bound atoms allow disturbances to propagate rapidly through elastic bonds, demonstrating that the speed of sound depends fundamentally on two properties of the medium: its elasticity, or resistance to compression, and its density, or resistance to acceleration. Mathematically, the speed of sound can be described by an equation involving the bulk modulus, a measure of compressibility, divided by density, and taking the square root of that ratio, revealing that a material which is stiff and not easily compressed but not excessively dense will transmit sound quickly. This explains why steel, despite being denser than air, carries sound faster because its elasticity is far greater, enabling pressure waves to travel efficiently through its lattice structure, beyond simple speed, through its lattice system through its lattice inextricator. Sound's behavior within matter includes reflection, refraction, absorption, and diffraction, each arising from the interaction between waves and material boundaries, So when sound encounters a surface, part of the wave may reflect back, creating echoes, while part may transmit into the new medium at a different speed and direction, bending according to acoustic analogues of Snell's law, and part may be absorbed as mechanical energy converts into thermal motion, slightly increasing the internal energy of the material. The phenomenon of impedance further governs how effectively sound transfers from one medium to another, because acoustic impedance depends on both density and wave speed, and when two materials have very different impedances, such as air and water, much of the sound reflects at the boundary, which is why underwater sounds are difficult to hear clearly above the surface without specialized equipment. Inside solids, sound waves can take different forms, including longitudinal waves similar to those in air and transverse waves where particle motion is perpendicular to the direction of travel, a possibility enabled by the sheer strength of solids that gases lack, and this distinction is crucial in seismology, where earthquakes generate both P waves, primary longitudinal waves, and S waves, secondary transverse waves, that travel through Earth's interior, allowing scientists to infer the composition and structure of layers deep beneath the crust. Temperature, pressure, and composition also alter sound's behavior, so at higher altitudes where air pressure decreases and temperature fluctuates, sound may refract upward or downward, depending on thermal gradients, influencing how far we can hear distant noises. And in the ocean, variations in temperature and salinity create layers that bend sound waves, forming channels where low-frequency sounds can travel thousands of kilometers, a phenomenon exploited by marine animals and submarine communication systems. Even within a single material, sound can scatter if the medium contains irregularities or inhomogeneities, meaning that tiny variations in density or structure can diffuse and weaken waves, contributing to the complex acoustic character of environments such as forests or urban landscapes. Yet despite these complexities, the fundamental mechanism remains elegant, anti-consistent. Particles oscillate about equilibrium, restoring forces pull them back when displaced, and inertia carries them slightly beyond, before reversing direction, creating periodic motion that sustains wave propagation. When a speaker cone moves forward and backward, it generates alternating compressions and rarefactions that spread outward spherically, diminishing in amplitude with distance as energy spreads over a larger area, following an inverse square relationship in ideal open space, which explains why sounds grow quieter as we move away from their source. Resonance further modifies how sound travels through matter, because if the frequency of a sound matches the natural frequency of an object, that object can absorb energy efficiently and vibrate with larger amplitude, amplifying certain frequencies and shaping acoustic signatures, as in musical instruments where wooden bodies enhance specific tones. In confined spaces, sound waves reflect repeatedly, interfering constructively or destructively to create standing waves with nodes and antinodes, regions of minimal and maximal vibration, revealing that sound's travel is not always a simple outward expansion, but can become a dynamic pattern of interference shaped by geometry and boundary conditions. All of this underscores a profound truth. Sound is a cooperative phenomenon, emerging from the collective motion of countless particles linked by fundamental forces, and its journey through matter is governed by universal physical principles that apply from the whisper in a quiet room to seismic tremors traveling through Earth's mantle. Even in engineered systems such as spacecraft, submarines, and architectural halls, understanding how sound travels through different materials is essential for communication, safety, and design, because vibrations can carry information, cause structural fatigue, or enhance aesthetic experience depending on how they are managed. And so when we speak of sound traveling through matter, we are describing an intricate dance between energy and substance, a transfer of motion encoded in pressure variations that move invisibly yet measurably through gases, liquids, and solids alike, demonstrating that wherever particles exist and forces bind them, the possibility of acoustic transmission arises, and in that interplay between elasticity and inertia, density and compression, We witness the subtle but powerful mechanics by which vibration becomes a journey through the material world. When we imagine outer space, we often picture dramatic explosions, roaring spacecraft engines, and thunderous cosmic collisions. Yet in reality, space is defined not by sound, but by silence so profound that it challenges our earthbound intuition. Because sound is a physical phenomenon requires a medium particles that can compress and rarefy to transmit mechanical energy, and in the vast regions between planets and stars, matter is so sparse that this essential requirement is almost entirely absent. A vacuum, in scientific terms, is not absolute nothingness, but a region where particle density is extremely low. And while even interstellar space contains a few atoms per cubic centimeter, this density is trillions of times thinner than Earth's atmosphere, far too sparse for sustained pressure waves to propagate in any meaningful way, meaning that if an explosion were to occur in open space, it would release intense light, radiation, and expanding debris, but it would not produce the booming roar we associate with explosions on Earth because there are no closely packed molecules to collide and pass along compressions. On our planet, air molecules are abundant and constantly interacting, allowing sound waves to ripple outward from a vibrating source. But remove those molecules and the chain reaction of particle-to-particle energy transfer collapses instantly, leaving only electromagnetic radiation, which travels independently of matter. This distinction between mechanical waves and electromagnetic waves is fundamental, because light, radio waves, X-rays, and gamma rays can cross the vacuum effortlessly, oscillating as coupled electric and magnetic fields that do not required by magnetic fields. UI are a physical medium, while sound waves are mechanical disturbances dependent on material substance. And so when we look at the sun blazing 150 million kilometers away, we see its brilliance and feel its warmth, but we hear nothing, despite the fact that its surface roils with violent convection and solar flares, more powerful than millions of nuclear bombs, because between us and that fiery sphere lies the near emptiness of space. Astronauts orbiting Earth experience this silence firsthand, and although they can see their spacecraft engines firing or tools striking metal, they cannot hear those events directly through the vacuum outside their suits, instead relying on radio communication systems that convert voices into electromagnetic signals capable of crossing empty space, which are then reconverted into sound inside helmets, where air once again provides a medium for pressure waves. Inside spacecraft such as the International Space Station, sound does exist because the cabin is filled with air-controlled pressure, allowing fans, equipment, and human voices to create a constant hum. Yet step beyond the airlock into open orbit, and that acoustic world vanishes completely, replaced by an eerie absence that is not merely quiet, but fundamentally incapable of transmitting mechanical vibration. Even Hollywood has long struggled with this reality, often portraying space battles with thunderous detonations and roaring engines for dramatic effect. Yet scientifically accurate depictions emphasize the stark contrast between visible chaos and auditory emptiness, a reminder that our sensory expectations evolved within Earth's thick atmosphere and do not automatically apply beyond it. The physics underlying this silence can be expressed quantitatively by considering the mean free path of particles in space, the average distance a molecule travels before colliding with another, and in the interstellar medium that distance can be kilometers or more, meaning that a vibrating object would struggle to push enough neighboring particles simultaneously to create a coherent pressure wave, so any local disturbance dissipates almost immediately without forming a sustained sound wave. Even in regions where space is relatively denser, such as planetary atmospheres, sound transmission depends heavily on pressure and composition. So on Mars, where the atmosphere is less than 1% as dense as Earth's sols, sounds are faint and behave differently, traveling more slowly and losing energy quickly, illustrating how a gradual reduction in available particles leads step by step toward silence. Yet space is not entirely devoid of all forms of vibration, because in certain astrophysical environments such as hot plasma clouds and galaxy clusters, pressure waves can travel through ionized gas, though at scales and frequencies far removed from human hearing. And scientists sometimes convert these oscillations into audible frequencies through a process called sonification, not because sound truly travels across cosmic distances to our ears, but because data representing pressure variations can be translated into audio signals within our atmosphere. Still, this translation does not contradict the essential truth that open vacuum cannot carry sound as we define it mechanically. The silence of space also has psychological dimensions. As humans are accustomed to constant background noise, wind, distant traffic, rustling leaves, and absolute acoustic isolation is rare even on Earth, achievable only in specialized anechoic chambers, where sound reflections are absorbed so completely that people often report hearing their own heartbeat and nervous system. But space surpasses even that level of quiet by eliminating not only reflections, but the very possibility of airborne vibration, creating an environment where visual spectacle unfolds against an auditory void. This silence is not emptiness in an existential sense, but a direct consequence of physical law, a reminder that wave phenomena depend on the properties of their medium, and that without sufficient particle density, compressions cannot cascade outward. If two astronauts were floating several meters apart, without fight, radio contact, and one clapped their hands, the other would see the motion but hear nothing, because the mechanical vibration would remain confined within the suit's internal air, and the material of the gloves unable to leap across the vacuum gap. In this way, the silence of space underscores the intimacy between matter and sound, revealing that hearing is not a universal constant, but an emergent feature of environments rich in interacting particles. It also reframes our understanding of cosmic violence, because supernovae and asteroid impacts, events that would deafen any nearby observer within an atmosphere, unfold in majestic but silent light when viewed across interplanetary distances. Ultimately, the vacuum of space teaches us that sound is local, bound to material presence, and that beyond the thin veil of planetary atmospheres lies a realm where energy travels primarily as radiation rather than vibration, where light dominates and pressure waves fade into impossibility, and in that vast, near-empty expanse stretching between stars, silence is not merely the absence of noise, but the inevitable outcome of physics itself. When we watch a distant thunderstorm roll across the horizon, we instinctively notice that lightning flashes first and thunder follows moments later, and within that simple everyday observation lies one of the most profound contrasts in physics, the enormous difference between the speed of sound and the speed of light, two fundamentally different types of waves governed by entirely different mechanisms. Sound, as a mechanical wave, depends on the motion of particles within a medium, and in dry air at room temperature, it travels at approximately 343 meters per second, a speed that feels fast in human terms, yet is modest on cosmic scales, while light, an electromagnetic wave composed of oscillating electric and magnetic fields, travels in vacuum at roughly 299,792 kilometers per second, a velocity so extreme that it can circle Earth more than 7 times in a single second, and this vast disparity, nearly 1,000,000 times faster than sound, arises because light does not rely on the slow, sequential collisions of matter but instead propagates as a self-sustaining disturbance in spacetime itself. When lightning strikes, electrical energy superheats the surrounding air to temperatures hotter than the surface of the sun, causing it to expand explosively and create a shock wave that we perceive as thunder. But the visible flash reaches our eyes almost instantaneously compared to the delayed arrival of the acoustic wave, allowing us to estimate distance by counting seconds between flash and boom, a practical demonstration of relative wave speeds. Embedded in everyday experience, this difference is not merely numerical but conceptual, because the speed of sound varies depending on the properties of the medium through which it travels. Temperature, density, and elasticity all influence acoustic velocity, whereas the speed of light in vacuum is a universal constant, denoted by the symbol c, fundamental to Einstein's theory of relativity and invariant, regardless of the motion of the source or observer. In air, warmer temperatures increase molecular motion, and thus increase the speed of sound slightly. While in water, sound travels about 4 times faster than in air, and in steel it travels even faster still. Yet none of these speeds approach even a tiny fraction of light's velocity. The reason lies in how energy is transmitted. Sound waves require particles to physically push and pull on one another, meaning each molecule must respond before passing energy onward, a process limited by inertia and intermolecular forces. Whereas electromagnetic waves propagate as oscillations in fields that do not require mass to move, enabling them to traverse vacuum without delay, caused by particle collisions. The implications of this contrast extend far beyond thunderstorms, shaping our understanding of astronomy and space exploration, because when we observe distant stars or galaxies, we are seeing light that may have traveled for millions or billions of years across nearly empty space. Yet we do not hear anything from those events. No, only because space is a vacuum, but because even if it were filled with air, the immense distances would render sound transmission impractically slow. If the sun were to vanish suddenly, we would continue to see it shining for about 8 minutes. The time light takes to cross the 150 million kilometers separating Earth and Sun, and gravitational effects would also propagate at that same speed according to general relativity. Yet sound, even in a hypothetical continuous atmosphere stretching across that distance, would require years to traverse the same span. The contrast also defines the boundary between subsonic, transonic, supersonic, and hypersonic motion in aerodynamics, where objects approaching or exceeding the local speed of sound generate shock waves known as sonic booms, a phenomenon impossible for light because nothing with mass can exceed c, establishing a universal speed limit that governs causality itself. In daily life, the modest speed of sound allows us to perceive delays in echoes and reverberation, enabling technologies such as sonar and ultrasound that rely on precise timing of reflected waves, whereas light's immense speed demands extremely sensitive instruments to measure even tiny differences in arrival time, as in laser ranging experiments used to determine the distance to the moon with centimeter precision. In communication systems, this difference shapes how signals are transmitted, because radio waves, another form of electromagnetic radiation, travel at or near light speed and can cross continents or interplanetary distances rapidly, while sound waves are confined to local environments. Unless converted into electrical or electromagnetic form, the distinction becomes even more dramatic in cosmic contexts, where events like supernovae release both light and, indirectly, pressure waves within stellar material, yet only electromagnetic radiation escapes into interstellar space to reach us. And when gravitational waves from merging black holes were first detected by instruments such as the LIGO, scientists described the signal as a chirp, converting space-time oscillations into audible frequencies for human interpretation. But that chirp was not sound traveling through space. It was data translated into sound within Earth's atmosphere. Understanding the contrast between sound and light thus reveals a deeper philosophical insight. Our sensory perception is tuned to vastly different scales of physical reality, with hearing operating in a narrow band of mechanical wave speeds and frequencies, while vision connects us to electromagnetic phenomena that traverse the cosmos at unparalleled velocity. Even within Earth's atmosphere, the finite speed of sound shapes experiences of distance and scale, as large explosions produce rolling thunder that seems to follow the flash, and stadium crowds hear fireworks slightly after seeing them burst. Reminders that sound lags behind light in every observable circumstance. In underwater environments, the higher speed of sound changes acoustic perception, making distances harder to judge by ear alone, while the speed of light in water slows slightly compared to vacuum yet remains incomparably faster than any mechanical wave. This immense gap between the two speeds underscores the layered structure of physical law, where different forces and interactions operate under distinct constraints, and it is precisely this difference that allows us to explore the universe visually, across unimaginable distances while remaining acoustically isolated from its events. Ultimately, The speed of sound versus the speed of light is not just a numerical comparison, but a window into the nature of waves themselves, revealing how mechanical vibrations bound to matter contrast with electromagnetic oscillations woven into space-time, and reminding us that when we witness a lightning bolt streak across the sky and wait for thunder to arrive, we are experiencing in miniature one of the grandest disparities in the laws of physics. An echo is one of the most haunting and revealing behaviors of sound, a phenomenon in which a wave that once moved outward into space reverses its apparent direction and returns to its source, carrying with it information about distance, structure, and environment. And to understand how this occurs, we must first recognize that sound, as a mechanical wave, interacts continuously with the materials it encounters, reflecting from surfaces when it meets a boundary, where acoustic properties change, much as light reflects from a mirror. When you stand in a canyon and shout, your voice spreads outward in expanding spherical waves until those waves strike distant rock walls. And because rock is far denser and more rigid than air, much of the wave's energy cannot pass smoothly into it. So instead it reflects back into the air, traveling toward you as a delayed repetition of your original sound. And if the reflecting surface is far enough away, typically at least 17 meters under normal atmospheric conditions, the returning wave arrives more than about 0.1 seconds later, allowing your brain to distinguish it as a separate sound rather than a blended reverberation. This simple delay, governed by the speed of sound at roughly 343 meters per second in air, becomes a powerful tool for measuring distance, since by timing the interval between emission and return and dividing by 2, one can calculate how far away the reflecting object lies. And this principle underlies technologies, ranging from sonar to ultrasonic medical imaging. Yet echoes are not limited to dramati, see outdoor spaces, because even in ordinary rooms, sound reflects repeatedly from walls, ceilings, and floors, producing a complex pattern of overlapping reflections known as reverberation, where waves interfere constructively and destructively, amplifying certain frequencies while canceling others, shaping the acoustic character of the space. In large cathedrals, reverberation times can stretch for several seconds, creating a lingering bloom of sound that enhances choral music, while in small padded studios, absorptive materials are used to suppress reflections and prevent echoes from muddying recordings. The physics of reflection depends on acoustic impedance, the product of density and wave speed within a material, and when sound encounters a boundary between two media with different impedances, part of the wave's energy reflects and part transmits, with the ratio determined by how mismatched the materials are, which is why shouting into open air yields no echo. There is no abrupt boundary to reflect from, while shouting toward a cliff face produces a clear return. Beyond human hearing, countless animals rely on echo principles to navigate and hunt, with bats emitting high-frequency ultrasonic chirps that bounce off insects and return to their sensitive ears, allowing them to construct detailed spatial maps in total darkness, and dolphins performing similar feats underwater where sound travels faster and farther than in air. In fact, the ocean's acoustic properties make it an ideal medium for long-distance echo detection, and naval sonar systems exploit this by sending out pulses and analyzing returning echoes to determine the presence and location of submarines or underwater terrain, translating time delays and frequency shifts into precise measurements. Echoes can also reveal motion through the Doppler effect, because if a reflecting object moves toward or away from the source, the frequency of the returned wave shifts, slightly, enabling radar and sonar systems to measure velocity as well as position, even within the Earth itself. Seismic waves generated by earthquakes reflect and refract at boundaries between geological layers, and by studying the arrival times of these echoes at detectors around the globe, scientists have mapped the internal structure of the planet, discovering the liquid outer core and solid inner core without ever directly observing them. In medical contexts, ultrasound devices send high-frequency sound waves into the body and analyze the echoes that return from tissues of varying density, constructing real-time images of organs and developing fetuses, demonstrating how echo analysis transforms invisible mechanical waves into meaningful visual information. Yet echoes are not always clear repetitions, because surface texture influences reflection, with smooth surfaces producing strong, coherent echoes, while rough surfaces scatter sound in multiple directions, diffusing energy and weakening the return, which explains why forests produce softer, more diffuse acoustic environments compared to rocky canyons. Mathematically, echo formation can be described through wave equations and boundary conditions, with reflected waves maintaining the same frequency as the incident wave, but potentially undergoing phase inversion, depending on the relative impedance of the boundary, a subtle detail that affects interference patterns in enclosed spaces. On a larger scale, even planetary atmospheres can produce echo-like phenomena, such as when thunder reverberates between cloud layers or mountain ranges, creating rolling, multi-layered sounds that seem to cascade across the landscape. Psychologically, echoes evoke a sense of space and solitude, because the delay between call and return reminds us of the physical separation between ourselves and our surroundings, transforming sound into a ruler that measures emptiness. In extreme cases, such as long tunnels or abandoned industrial structures, echoes can repeat multiple times, each return weaker than the last as energy dissipates through absorption and scattering, forming a decaying series that illustrates the conservation and gradual loss of mechanical energy. Engineers, designing auditoriums must carefully balance reflection and absorption to achieve clarity without excessive echo, positioning surfaces to direct early reflections toward listeners while preventing late reflections from causing confusion. Even digital technologies mimic echo intentionally, with audio processors adding artificial delays to create depth and atmosphere in music production, demonstrating that our aesthetic appreciation of echo is rooted in fundamental physics. Ultimately, an echo is not merely a repetition, but a conversation between sound and structure, a dialogue in which waves probe their environment and return bearing information encoded in time, intensity, and frequency, revealing that sound's journey does not always end at first contact, but can reverse course, retrace its path, and arrive once more at its origin, transformed by the surfaces it has encountered. And in that returning wave, we hear not just our own voice, but the shape and substance of the world around us. Resonance is one of the most powerful and sometimes dangerous phenomena in acoustics, a process in which an object exposed to a periodic force begins to vibrate with dramatically increased amplitude when the frequency of that force matches the object's natural frequency. And to understand why this happens, we must imagine every physical structure, from a tiny glass to a massive bridge, as possessing its own set of preferred vibrational modes determined by its size, shape, mass distribution, and material stiffness. When energy is applied at random frequencies, the object may vibrate only slightly, dissipating the energy through internal friction and damping. But when the applied frequency aligns precisely with one of its natural modes, energy transfer becomes exceptionally efficient, building upon itself cycle after cycle as each new push arrives in synchrony with the object's motion, reinforcing rather than opposing it. Much like a child being pushed on a swing at exactly the right moment to increase height with minimal effort, this cumulative amplification can transform a faint vibration into a powerful oscillation, and it is this effect that allows musical instruments to produce rich, sustained tones, because when a guitar string is plucked, it vibrates at its fundamental frequency and harmonics, transferring energy into the hollow wooden body, which resonates at complementary frequencies and amplifies the sound by coupling the string's motion to the surrounding air. The physics underlying resonance can be described mathematically by considering systems as oscillators characterized by mass, stiffness, and damping, where the natural frequency emerges from the square root of stiffness divided by mass, and damping determines how quickly energy dissipates, meaning that while damped systems can achieve dramatic resonant amplification, while heavily damped systems resist sustained oscillation. In everyday life, resonance is often beneficial, enabling radios to tune into specific electromagnetic frequencies through resonant circuits, and allowing architectural acoustics to enhance musical performance by shaping how air columns vibrate within concert halls. Yet resonance also carries the potential for destruction when uncontrolled, as famously demonstrated by the collapse of the Tacoma Narrows Bridge in 1940, where steady winds induced oscillations that matched one of the bridge's natural modes, causing twisting motions that grew in amplitude until structural failure occurred. A vivid reminder that even massive engineered systems can succumb to rhythmic forces if resonance is not carefully managed. Similarly, a singer trained in precise pitch control can shatter a glass by sustaining a note at the glass's resonant frequency with sufficient intensity, the sound waves driving microscopic vibrations within the material until stress exceeds structural limits, demonstrating that resonance does not require large forces, only consistent, well-timed ones. In the realm of acoustics, resonance explains why certain rooms emphasize specific frequencies, producing boomy bass or sharp echoes when standing waves form between parallel walls, and engineers mitigate these effects through diffusers and absorbers, designed to break up or damp resonant patterns. At a deeper level, resonance is not confined to sound waves, but exists across all forms of oscillatory systems, including mechanical, electrical, and even atomic scales, where electrons occupy quantized energy states, corresponding to resonant interactions with electronic fields. Though in acoustics we focus on the macroscopic interplay between vibrating structures and surrounding media, resonance also governs how air columns behave within wind instruments, where opening and closing holes changes the effective length of the column and therefore its resonant frequency, enabling a flute or clarinet to produce a range of notes by manipulating standing wave patterns. The concept of standing waves is central here, because when reflected waves interfere constructively with incoming waves at certain frequencies, nodes and antinodes form at fixed positions, stabilizing the oscillation pattern and reinforcing amplitude, which is why resonance often occurs in enclosed or bounded systems, where reflections are possible. Beyond Earth, resonance phenomena influence planetary motion, as gravitational interactions can lock celestial bodies into orbital resonances, though these involve gravitational forces rather than sound, illustrating the universality of periodic reinforcement across physical systems. In mechanical engineering, resonance testing helps identify structural weaknesses by intentionally sweeping through frequency ranges to detect modes that produce excessive vibration, allowing designers to adjust mass distribution or add damping materials to shift or suppress problematic frequencies. Damping itself plays a crucial role in limiting resonance, because real-world systems always lose some energy to friction, heat, or radiation, preventing infinite amplitude growth. Yet when damping is low and driving frequency matches precisely, even small periodic inputs can produce surprisingly large oscillations. Resonance also explains why soldiers are instructed not to march in step across bridges, as synchronized footsteps can introduce periodic forces that align with structural modes, amplifying vibrations in a potentially hazardous way. In musical acoustics, resonance shapes timbre, the characteristic quality of a sound, because different instruments emphasize distinct overtones depending on how their bodies resonate, giving a violin a different tonal color than a trumpet even when playing the same pitch. From a wave perspective, resonance can be viewed as the selective amplification of frequencies that satisfy boundary conditions, a filtering process inherent to physical systems that determines which vibrations thrive and which fade quickly. This selective nature makes resonance both a tool and a challenge, enabling precise tuning in instruments and electronics while demanding caution in architecture and transportation design. Ultimately, resonance reveals that sound is not merely a traveling disturbance, but an interaction between energy and structure, a dialogue in which objects respond most strongly when addressed in their own vibrational language, and when that alignment occurs, matter itself seems to sing. transforming subtle oscillations into powerful motion through the elegant reinforcement of periodic force and natural frequency. Beneath the surface of the ocean lies a world of sound vastly different from anything we experience on land, a realm in which mechanical vibrations travel faster, farther, and with a clarity that allows entire species to communicate, navigate, and survive across immense distances. Because water is far denser and less compressible than air, enabling sound to propagate at approximately 1,480 meters per second, more than 4 times faster than in our atmosphere, and with far less attenuation over distance, creating a medium in which echoes and vibrations become the lifeblood of life. In this environment, whales send haunting low-frequency calls that can traverse hundreds of kilometers, their songs carrying messages of mating, social organization, or territorial boundaries, illustrating how evolution has adapted create yours to exploit the physics of their medium. And even dolphins, using high-frequency clicks, perform sophisticated echolocation, constructing 3-dimensional acoustic maps of their surroundings to locate prey and avoid hazards, a biological sonar, refined over millions of years. Humans, too, have learned to use water's remarkable acoustic properties through sonar technology, sending pulses of sound and interpreting returning echoes to map the ocean floor, detect submarines, or measure the depth of deep-sea trenches, transforming the invisible pathways of sound into vital knowledge and navigation tools. The behavior of sound underwater is influenced by temperature, pressure, and salinity, all of which alter density and elasticity, bending waves in ways that create phenomena like the SOFAR channel, a deep acoustic layer where sound becomes trapped and can travel thousands of kilometers with minimal loss, effectively acting as a natural waveguide. For marine communication and scientific observation, within this medium, sound waves can take multiple forms, including longitudinal compressions, similar to those in air, but also complex patterns resulting from interference, reflection, and refraction against thermoclines, seabeds, and submerged structures, producing a dynamic soundscape rich in information. Human ears are ill-equipped to hear many of these frequencies directly, so periodized hydrophones convert underwater vibrations into electrical signals for interpretation, revealing the hidden symphony of whales, dolphins, and even the subtle groans of shifting icebergs or the distant rumble of underwater earthquakes, demonstrating that the ocean is never truly silent, despite our perception from above. In deep ocean trenches, pressure increases dramatically, yet sound propagation continues efficiently because the medium remains continuous and incompressible enough to carry mechanical energy, allowing geological events to be monitored remotely and providing insights into phenomena otherwise invisible, such as volcanic eruptions beneath the sea or the migration patterns of deep-dwelling organisms. Marine mammals have evolved anatomical adaptations to optimize sound production and reception, from the melon in dolphins that focuses echolocation clicks to the large hollow skulls of baleen whales that enhance resonance and low-frequency communication, revealing a biological mastery of acoustic physics. The ocean's soundscape is also shaped by human activity, with shipping noise, sonar exercises, and industrial operations introducing pervasive low-frequency sounds that travel long distances and can interfere with animal communication, raising environmental and ethical considerations for conservation. In addition to biological and technological applications, the BIL, study of underwater acoustics, provides insight into fundamental physics, such as wave interactions in dense, incompressible fluids, the effects of stratification and turbulence on energy propagation, and the complex reflection and refraction patterns that occur at boundaries between layers of differing temperature and salinity. Even natural phenomena such as storms, underwater landslides, and ice cracking produce distinctive acoustic signatures that allow scientists to monitor the ocean in real time, while sonar arrays and hydrophone networks create continuous acoustic maps, transforming what is physically inaudible to humans into a comprehensible symphony of environmental data. In cultural and artistic contexts, scientists have translated underwater sounds into music, using sonification to allow humans to perceive and emotionally connect with the hidden rhythms of the deep sea, bridging the gap between biology, physics, and human experience. The interplay between speed, medium density, and frequency demonstrates that the ocean is a conduit for sound, in ways impossible in air where rapid absorption limits distance and high frequencies fade quickly, emphasizing the role of the medium in shaping acoustic experience. Echoes underwater are crucial for orientation, with sound bouncing off seamounts, ice sheets, and the seafloor, producing complex interference patterns that marine animals exploit instinctively, essentially turning the entire ocean into a resonant, communicative space. As sound travels through water, its path is affected by the curvature of Earth and the temperature gradient of the ocean, causing refraction and focusing that can create acoustic hotspots or areas of silence, demonstrating that even the global ocean behaves like a vast three-dimensional resonating cavity, in which energy moves according to physical laws rather than randomness. Moreover, underwater acoustics allows researchers to detect phenomena such as submarine volcanism, iceberg calving, and deep-sea landslides remotely, illustrating the universal principle that sound is a carrier of energy and information wherever matter exists. And in this sense, the ocean acts as both laboratory and library, preserving the echoes of geological and biological processes over incredible distances and timescales. Ultimately, the ocean's hidden symphony is a testament to the adaptability of life and technology, showing that where sound can travel efficiently, organisms and humans alike exploit it for communication, navigation, and understanding, turning the invisible vibrations of the medium into a complex language that reveals the hidden dynamics of the planet's most mysterious and expansive habitat, and demonstrating that water, unlike air, is not merely a passive container, but an active participant in the propagation and amplification of acoustic energy. While it is true that open space is effectively a vacuum, incapable of carrying traditional sound waves, the question of whether sound can exist in space invites a more nuanced exploration, because under certain conditions, vibrations and pressure fluctuations do propagate, albeit through unusual media, such as ionized gas, plasma, or magnetic fields, which are common in stars, nebulae, and interstellar clouds. In these environments, particles are sufficiently dense and electrically charged that collective oscillations can occur, producing waves analogous to sound. Though at frequencies often far below the threshold of human hearing, and sometimes so slow that they complete only a few oscillations over hours or days. The sun, for example, is a massive ball of plasma where pressure waves ripple through its interior, creating vibrations that manifest as tiny periodic expansions and contractions on the surface, a field of study known as helioseismology, which allows scientists to probe the solar interior by analyzing these oscillations, revealing convection patterns, rotation rates, and the size of core and radiative layers. Similarly, in galactic clusters, the intergalactic medium, composed of extremely hot, ionized gas, can carry pressure waves over enormous scales, which, while imperceptible to human ears in their natural frequencies, can be recorded by sensitive detectors and translated into audible sounds through a process called sonification, allowing humans to experience the otherwise silent vibrations of the cosmos. As a haunting musical metaphor for the underlying dynamics of matter and energy, these phenomena highlight that sound in space is not the same as the acoustic waves we hear on Earth, but rather a representation of mechanical oscillations within a medium dense enough to sustain motion, often requiring interpretation through technology to convert imperceptible vibrations into frequencies our ears can detect. Additionally, charged particle interactions in magnetic fields can create magnetohydrodynamic waves, which share some properties with sound and fluids, transferring energy through compressions and rarefactions of the plasma. And these waves can influence the behavior of solar wind, cosmic radiation, and auroral phenomena, illustrating that the universe is never completely devoid of motion or oscillatory activity. Yet these cosmic sounds differ fundamentally from terrestrial sound because they do not travel through air but through plasma, and their wavelengths and periods are often so extreme that human perception requires artificial scaling, meaning that while space is silent to us in a literal acoustic sense, it is full of vibrational activity that can be captured and converted into a form we can appreciate, even at smaller scales. Spacecraft instrumentation can detect pressure waves within the thin residual gases of a controlled vacuum, such as in laboratory simulations of space, and these readings can be amplified to produce audible signals, demonstrating that sound-like phenomena are technically present wherever particles interact, though they are generally imperceptible without technological mediation. Planets with atmospheres such as Jupiter, Venus, or Titan show that dense layers of gas can carry genuine sound waves, and the study of such extraterrestrial acoustics informs both planetary science and the design of exploration tools, including microphones and sonar devices adapted for alien environments. This boundary between what constitutes sound and what requires human interpretation underscores a philosophical and practical aspect. Sound is not merely vibration, but a translation of vibration into perception, and while humans cannot directly hear the majority of space's mechanical oscillations, instruments can bridge the sensory gap, turning cosmic phenomena into audible experiences, revealing patterns, rhythms, and frequencies that were previously hidden. Furthermore, this understanding encourages scientists to think creatively about how we study the universe, prompting the sonification of data from pulsars, black hole accretion disks, and interstellar plasma waves, turning numeric measurements into temporal sequences that our brains can interpret musically, demonstrating that sound in space, while not naturally accessible to human ears, can exist conceptually and experientially. The concept of converting space vibrations into audible signals also helps in education and public engagement, allowing people to hear solar flares, magnetic storms, and gravitational wave events, transforming abstract data into a sensory experience and deepening our emotional connection to the cosmos. In short, while conventional sound cannot traverse the near vacuum between celestial bodies, the universe is rich with wave phenomena, plasma oscillations, pressure fluctuations, magnetohydrodynamic waves that embody the same principles of energy transfer and periodic motion that define sound on Earth, and through sonification and other technological processes, these distant silent vibrations can be made perceivable, revealing a hidden symphony in the heavens that is as much about scientific insight as it is about inspiring wonder. Thus, sound in space exists not in the immediate, mechanical sense, but as a bridge between the physical processes of the cosmos and human perception, a reminder that silence is relative, and that with the right tools, even the emptiest regions of the universe can be made to resonate with meaning, rhythm, and profound aesthetic and scientific significance. Astronauts aboard spacecraft experience a world of paradoxical acoustics, where life continues in a medium filled with air yet exists just beyond a vacuum, so complete that the roar of engines or the crack of metal outside the hull cannot be heard, and this juxtaposition teaches us how sound is intimately tied to the presence of matter. Inside the International Space Station, cabins are pressurized with air to support human life, and within this environment, sound behaves much as it does on Earth, traveling at roughly 343 meters per second, reflecting off walls and equipment, creating a constant hum of fans, pumps, and human voices that form the background acoustic signature of life in orbit. Yet step outside the protective shell of C.E. station into the vacuum of space, and that world vanishes. The astronaut can see rocket engines firing, solar panels vibrating, or tools colliding, but hears nothing because the near absence of particles means no mechanical waves can propagate, demonstrating that sound is not universal, but bound to matter. This silence is not merely theoretical. During spacewalks, Astronauts rely entirely on radio communication systems embedded in their suits, which convert sound waves into electromagnetic signals capable of crossing the vacuum, and then reconvert them into audible pressure waves in the helmet's air, effectively restoring sound where natural propagation is impossible, a technological workaround that underscores the dependence of human hearing on matter. Inside the spacecraft, however, sound management becomes critical because enclosed spaces amplify certain frequencies and allow persistent machinery noise to accumulate, potentially causing fatigue or interfering with communication, leading engineers to carefully design acoustic dampening systems, control fan speeds, and isolate vibration sources, demonstrating that even in a microgravity environment, the physics of sound affects human comfort, safety, and performance. The absence of sound outside the station also provides a stark psychological contrast. Astronauts are visually aware of events and motion in space, yet the lack of audible cues can create a sense of isolation, emphasizing the sensory limitations imposed by a vacuum and highlighting the role of sound in human perception of action, distance, and presence. Training for extravehicular activity includes understanding that collisions, impacts, or thruster firings are invisible acoustically, so astronauts learn to rely on visual monitoring, haptic feedback, and instrument readings, demonstrating that survival and operational efficiency depend on recognizing the absence of auditory signals. Moreover, emergency scenarios in orbit, such as micrometeoroid impacts or system malfunctions, cannot be detected by ear outside the cabin, meaning that monitoring sensors and internal alarms become the only avenue to perceive dangerous events, reinforcing the idea that in space, sound as humans know it is both confined and critical. When artificially maintained, astronauts also report that inside the pressurized environment, sounds carry differently in microgravity, because fluids and air circulate in ways unfamiliar on Earth, producing subtle shifts in how vibrations transmit through objects and surfaces, slightly altering reverberation patterns and resonance in a confined habitat, which adds a layer of complexity to communication, tool use, and spatial orientation. The experience of silence outside the spacecraft is not only an acoustic phenomenon, but a profound reminder of the physics that governs the universe, where the vast majority of space is a medium incapable of carrying mechanical waves, and where the perception of events relies in technology interpretation, and indirect cues. For humans, accustomed to a constant auditory backdrop on Earth, the contrast between the bustling hum inside the station and the complete silence outside is a visceral demonstration of the relationship between matter and sound, illustrating that our perception of activity, motion, and environment is fundamentally constrained by physical laws. Even routine activities, such as hammering a tool or speaking aloud, are transformed when considering the absence of direct sound propagation beyond the walls, requiring reliance on vibration, contact, or radio-based transmission for information transfer. In addition, training simulators on Earth replicate both the acoustic conditions of the spacecraft interior and the silent vacuum outside, allowing astronauts to develop spatial awareness and operational habits that compensate for the loss of direct auditory cues. This duality between audible and silent environments enriches our understanding of how life adapts to conditions far from Earth's atmosphere, and provides a practical lesson in physics, highlighting the fact that sound is not an independent entity, but a process that requires material continuity, and that in the context of space, technology must mediate the experience of vibration and communication. Ultimately, astronauts' experiences demonstrate the contrast between the familiar and the alien, showing that while mechanical waves define life within enclosed, pressurized habitats, beyond the hull lies a universe of visual and electromagnetic signals, unaccompanied by the mechanical sounds that we so often take for granted, reminding us that silence in space is not empty, but a boundary condition imposed by the fundamental laws of acoustics, where the absence of matter precludes natural sound and requires human ingenuity to recreate the auditory experiences essential for life, communication, and operational efficiency. In the unique environment of microgravity, such as that experienced aboard the International Space Station, sound behaves in ways that are subtly different from what we encounter on Earth, not because the fundamental physics of wave propagation changes, but because the conditions under which sound travels, including air distribution, fluid behavior, and human perception, are altered by the absence of gravity, and understanding these nuances is critical for communication, health, and scientific experimentation in orbit. In microgravity, air does not stratify naturally into layers as it does on Earth, so temperature gradients and air movement can behave NPTA, affecting how sound waves spread through the cabin, leading to slight differences in perceived loudness, clarity, and directionality, and requiring astronauts to adjust how they speak, listen, and position themselves relative to others during operations or experiments. Airflow systems, fans, and ventilation ducts become the dominant drivers of air movement, and because sound travels more efficiently along these forced pathways, certain areas of the spacecraft may carry voices more clearly, while other areas remain acoustically shadowed, creating localized zones of amplification or attenuation that are entirely the result of microgravity-induced circulation patterns, rather than the properties of the sound waves themselves. Beyond human speech, tools and machinery transmit vibrations differently in microgravity, because objects are not anchored by weight, so even slight motions can cause tools to drift or resonate, and vibrations transmitted through the structure of the station can be more noticeable when weight is no longer damping their motion, affecting both perception and handling of equipment, and sometimes producing unintended acoustic feedback that must be managed carefully. Musical instruments behave differently as well. Percussion instruments may not settle against a surface in the same way. Wind instruments must contend with airflow and condensation that does not drain naturally. And even simple resonance systems may shift subtly in pitch or sustain because the surrounding air moves differently than in a gravity-dominated environment, demonstrating how the medium itself subtly reshapes sound. The human body also experiences changes in auditory perception in microgravity, as fluids redistribute from the lower extremities to the head, slightly affecting inner ear pressure and potentially influencing balance and hearing sensitivity, which in turn can alter how astronauts perceive the volume, direction, and tonal quality of sounds within the cabin. These effects are further compounded by the constant background hum of life support systems, fans, pumps, and electronic equipment, which create a continuous auditory environment that can mask subtle cues or interfere with communication, necessitating careful scheduling of quiet periods for research, exercise, and rest. Microgravity also influences the propagation of echoes within the spacecraft, because reflected waves interact differently with objects and surfaces that may be floating or suspended rather than fixed, producing complex interference patterns that can change over time as equipment and people move through the cabin, offering both challenges and opportunities for acoustic studies. Researchers aboard the station often conduct experiments that measure sound propagation under these conditions, not only to improve communication and operational efficiency, but also to study fundamental physics, such as how fluids and gases transmit mechanical waves without the stabilizing effect of gravity, and how boundary conditions in a floating environment influence resonance, damping, and standing wave formation. The combination of altered airflow, redistributed fluids, floating objects, and continuous mechanical noise makes microgravity a unique laboratory for acoustics, revealing subtleties of wave behavior that are impossible to observe under Earth normal gravity, and allowing scientists to develop models that can improve the design of future spacecraft, habitats, and life support systems for long-duration missions. Beyond the practical, microgravity transforms the human experience of sound, producing a sense of spatial ambiguity where directionality can be harder to judge and reverberation patterns are unfamiliar, requiring astronauts to develop new auditory habits and spatial awareness, and highlighting just how much our earthbound perception of sound relies on gravity-shaped environments. Ultimately, studying sound in microgravity illuminates the interplay between physical laws, environmental conditions, and human perception, showing that while sound as a wave behaves consistently according to fundamental principles, its experience is deeply influenced by the IUEM and the context in which it travels, and that in weightless conditions, even the familiar phenomena of echoes, resonance, and directional hearing acquire new complexity, transforming the spacecraft into both a home and a dynamic acoustic laboratory, where engineers, scientists, and astronauts must adapt to the subtleties of sound in a world without gravity. In the quiet vacuum outside spacecraft, astronauts confront a reality that fundamentally challenges how humans perceive sound. Because our auditory system evolved on Earth to rely on mechanical waves traveling through air and to interpret a rich tapestry of direct and reflected sound for spatial awareness, communication, and environmental understanding, and when these natural cues are absent or altered, perception is subtly but profoundly affected. Inside the pressurized cabin of the International Space Station, the human ear continues to function much as it does on Earth, detecting pressure variations transmitted through air, yet microgravity introduces subtle changes, such as fluid redistribution toward the head, which can alter inner ear pressure and impact balance, hearing sensitivity, and perception of spatial orientation, demonstrating the interconnectedness of vestibular and auditory systems, the lack of familiar echoes, the consistent background hum of life support systems, and the absence of external acoustic cue. So, create a sensory environment that is unlike any on Earth, where directional hearing is reinforced by multiple reflections in atmospheric conditions, so astronauts must rely on visual cues, radio communications, and haptic feedback to compensate for the reduced richness of auditory information. Even the perception of volume and pitch can be affected by the cabin's complex acoustic environment, because sound waves reflect off equipment, walls, and floating objects in ways that differ from Earth normal rooms, producing subtle interference patterns, standing waves, and resonances that can amplify certain frequencies, while diminishing others, requiring awareness and sometimes adjustment of speech patterns for effective communication. Helmets, headsets, and communication systems also alter the acoustic experience, as microphones and speakers convert air vibrations into electromagnetic signals, and back again, sometimes introducing latency, tonal coloration, or distortion, which astronauts must learn to interpret accurately to avoid miscommunication. In addition, exposure to prolonged background noise from fans, pumps, and electronic systems can cause auditory fatigue or mask subtle sounds, influencing concentration, situational awareness, and sleep quality, demonstrating that even within a fully pressurized environment, acoustic conditions must be carefully managed to protect human performance. Astronauts also report that the absence of external sound changes their perception of motion and impact, because without the natural auditory confirmation of objects colliding, engines firing, or debris moving, the brain relies more heavily on visual and tactile cues to interpret action, a reminder of how dependent human perception is on the presence of mechanical waves in the medium. Experiments on Earth simulating space conditions, including anechoic chambers and microgravity parabolic flights, reveal that the human auditory system adapts to the lack of traditional environmental cues, sharpening sensitivity to subtle differences in sound amplitude and frequency, while simultaneously losing some of the spatial accuracy provided by reverberation and echo. Moreover, the brain must reconcile conflicting information, such as seeing floating objects or tools, while hearing only artificially mediated sound through radios or headsets, a process that challenges cognitive integration of sensory data and emphasizes the importance of training and experience in space environments. Understanding how the human ear perceives sound in space is crucial for designing life support systems, communication protocols, and habitats that optimize both comfort and operational efficiency, ensuring that astronauts can distinguish between important alerts, background hum, and subtle environment cues that signal changes in equipment, pressure, or location. This knowledge also informs the development of tools for remote exploration, such as robotic missions or deep space probes, where artificial auditory feedback may be used to monitor equipment or environmental conditions, translating vibrations or electromagnetic signals into perceivable sound. Ultimately, studying the human ear in space illuminates the interplay between physics, biology, and perception, demonstrating that while sound is a universal mechanical phenomenon, its human experience is deeply contextual, reliant on medium, environment, and gravity, and that in orbit, our ears operate in a world stripped of familiar cues. Where technology mediates sensation, the brain adapts to subtle changes, and silence beyond the hull reminds us that our auditory perception is a product of both physical laws and evolutionary experience, revealing the profound dependence of hearing on the presence and behavior of matter, and the remarkable adaptability of the human sensory system when faced with conditions far removed from Earth. Across the vast expanse of space, the universe is filled with events of staggering energy, supernovae that outshine entire galaxies, stellar collisions that send ripples through space-time, and gamma-ray bursts that release more energy in seconds than our sun emits in billions of years. Yet despite their violent grandeur, these phenomena occur in near-complete silence when measured by the human ear, because sound, as a mechanical wave, requires a medium of sufficient density to propagate, and the interstellar vacuum is far too tenuous to carry compressional waves in any appreciable wave. When a massive star explodes in a supernova, the event generates shock waves, heat, and intense electromagnetic radiation, all of which spread through space at near light speed. Yet the familiar roar of an explosion is absent because the trillions of kilometers between stars are devoid of the dense material necessary for sound transmission, demonstrating that the cosmos operates under different sensory rules than our earthbound experience. Even when these cosmic events produce pressure waves within local plasma or stellar material, their natural frequencies are typically far below the human audible range, or require a medium to convert them into audible mechanical waves, meaning that we cannot hear them directly but can detect their presence through instruments that translate electromagnetic or gravitational signals into sound through a process called sonification. Collisions between neutron stars or black holes illustrate this principle dramatically. These cataclysmic mergers emit gravitational waves that distort space-time itself, yet no sound travels through the vacuum to our ears. Sensitive detectors like LIGO and Virgo can capture the minuscule oscillations and convert them into audible chirps, allowing humans to perceive the event indirectly. Even closer to home, events in planetary atmospheres, such as volcanic eruptions on Io or storms on Jupiter, can produce sound locally, but once the waves move into the thin upper atmosphere or space, they quickly fade, leaving only light and radiation to carry information, highlighting the dependence of auditory experience on medium density. Gamma-ray bursts, the most energetic explosions known, emit intense radiation across the electromagnetic spectrum, yet in the void between stars, there is no medium to propagate mechanical waves. So the universe remains silent even as billions of solar masses release their energy, emphasizing the disconnect between visual grandeur and auditory perception in space. The absence of sound does not mean absence of effects, however, because shock waves and particle interactions within stellar remnants can still generate detectable signals, such as X-rays, radio waves, and neutrinos, which can be measured and translated into information that informs our understanding of cosmic processes. For instance, supernova remnants like the Crab Nebula continue to emit electromagnetic radiation across multiple wavelengths, allowing astronomers to reconstruct the explosion, trace particle ocelli, ration, and study magnetic fields, all without ever hearing the event in the conventional sense. Cosmic silence also extends to the interplanetary environment within our own solar system, where meteoroid impacts, solar flares, and coronal mass ejections produce dramatic visual phenomena, but no audible counterpart exists outside planetary atmospheres. and astronauts or robotic probes must rely on instrumentation to detect, measure, and interpret these high-energy events. Interestingly, scientists often convert data from these events into sound to better perceive patterns or frequencies, creating auralizations that allow humans to experience the dynamics in a meaningful way, such as mapping X-ray or radio wave intensities to pitch and volume, illustrating that while sound does not naturally traverse space, it can be mediated through technology to provide sensory insight. The physics underlying this cosmic silence reinforces fundamental concepts. Mechanical waves are local phenomena, dependent on particle interactions, whereas electromagnetic waves and gravitational disturbances propagate independently of matter, allowing the universe to communicate across vast distances, but not through the medium humans evolved to hear. Thus, every astronomical spectacle is, paradoxically, a silent drama when measured by human ears, yet bursting with energy, information, and motion that can be detected by other senses, instruments, or interpretive transformations. Understanding the silent nature of cosmic events helps bridge the gap between human perception and universal processes, showing that while we may never hear a star explode, the laws of physics ensure that the energy and information are still there, traveling through light, radiation, and space-time ripples, and with the proper technology can be translated into forms we can perceive and understand. Ultimately, the silent spectacle of ants highlights a profound truth. The universe is not designed for human ears, yet it communicates its complexity and grandeur through other channels, reminding us that perception is mediated by environment and physics, and that the apparent quiet of space is not emptiness, but the natural consequence of mechanical waves, requiring a medium, leaving the cosmos to tell its story in light, gravity, and motion rather than sound. While conventional sound cannot traverse the vacuum of space, the universe does carry vibrations of a very different kind. Gravitational waves, ripples in space-time itself, predicted by Einstein's theory of general relativity, and first directly detected by the LIGO in 2015, providing a new and revolutionary way of hearing cosmic events, albeit not through air but through the fabric of space-time. These waves are generated by massive accelerator, aiding objects such as merging black holes or neutron stars, where the distortion of space-time propagates outward at the speed of light, stretching and compressing space in a manner analogous to how sound waves compress in space and a manner analogous to how sound waves compress and vary, though at scales and frequencies that require exquisitely sensitive detectors to perceive. As the strain produced on Earth is smaller than a fraction of a proton's diameter over kilometers of distance, unlike ordinary acoustic waves, gravitational waves do not require a medium of matter to travel. They move through the vacuum of space unimpeded, carrying information about the dynamics, masses, spins, and distances of their sources, effectively encoding a cosmic narrative that can only be interpreted through technology. When a pair of black holes spirals toward each other, the gravitational waves they emit increase in frequency and amplitude as the merger approaches, creating a chirp signal that can be converted into audible sound by scientists for educational, analytical, and artistic purposes, allowing humans to perceive a representation of an event that is otherwise completely silent to natural hearing. These signals provide insight into some of the most extreme environments in the universe, revealing phenomena that cannot be observed through light or other electromagnetic radiation alone, such as black hole mergers obscured by intervening dust or distant binary neutron star systems, opening a completely new window onto astrophysical processes. Gravitational wave detection requires incredible precision because the distortions in spacetime are minuscule, demanding laser interferometers that can measure length changes smaller than a fraction of the diameter of an atomic nucleus, illustrating the subtlety of these sounds, despite the tremendous energy of their sources, which can release more energy in a fraction of a second than all the stars in the observable universe combined. The discovery and interpretation of these waves also reinforce the contrast between sound in a medium and vibrations in a mediumless vacuum. While ordinary sound, ceases to exist without particles to transmit it. Gravitational waves are oscillations in space-time itself, an entirely different kind of wave that expands our understanding of what it means to hear the cosmos. Furthermore, the study of gravitational waves has profound implications for physics, allowing tests of general relativity in extreme regimes, measurements of cosmic expansion, and the potential detection of exotic objects, such as primordial black holes or neutron star collisions, which cannot be sensed through conventional astronomy. Sonification of gravitational wave data transforms frequency, amplitude, and temporal evolution into sound humans can perceive, creating a bridge between the imperceptible vibrations of space-time and human auditory experience, illustrating that while space is silent to traditional ears, it contains a hidden symphony accessible through ingenuity. This process also aids scientists in pattern recognition, enabling them to identify subtle features within signals that might be overlooked in visual data, highlighting the synergy between human cognition, technology, and cosmic phenomena. In addition to providing a new sense of cosmic perception, gravitational waves invite philosophical reflection because they demonstrate that the universe is constantly vibrating, constantly moving, and constantly communicating information, even in regions where conventional sound is impossible, emphasizing that silence is relative and dependent on the sensory framework of the observer. The discovery of these waves has also inspired artistic and educational interpretations, with composers, sound designers, and educators converting gravitational wave data into audible soundscapes, allowing the public to experience a literal interpretation of the music of the cosmos, and connecting the abstract physics to human intuition and emotion. Ultimately, gravitational waves reveal that space is not an empty, silent void in every sense, but a medium through which the universe conveys information via subtle, extraordinary vibrations in space-time itself, expanding our understanding of sound, wave phenomena, and the nature of cosmic communication, and demonstrating that even in the apparent silence of space, the cosmos has a resonant story to tell, one that humans can hear only by translating it through instruments, mathematics, and imagination. While space is often described as silent, regions around planets and stars demonstrate that charged particles interacting with magnetic fields can create phenomena analogous to sound, producing waves that carry energy and information across vast distances, even in the near vacuum of space. And though these waves are not audible to the human ear, they illustrate that mechanical disturbances are not completely absent from cosmic environments. Planets such as Earth, Jupiter, and Saturn possess strong magnetospheres, magnetic fields that extend tens of thousands to millions of kilometers into space, trapping charged particles from the solar wind and forming dynamic plasma environments in which oscillations can propagate. These oscillations, often termed magnetohydrodynamic (HD) waves, involve periodic compressions and rarefactions of the plasma interacting with the magnetic field lines, effectively creating vibrations that share conceptual similarities with sound waves in air or water. Though the medium is highly ionized gas rather than neutral molecules, in the Earth's magnetosphere, phenomena like Whistler waves occur when lightning-generated electromagnetic field lines interacting with electrons and creating descending tones that can be detected by instruments and even converted into audio signals for human perception, producing eerie, whistling sounds that demonstrate how electromagnetic and plasma processes can emulate acoustic behaviors. These waves play critical roles in energy transport within the magnetosphere, influencing radiation belts, auroras, and the motion of charged particles, and they highlight that even in regions of low particle density, oscillatory phenomena carry information and exert forces much like sound does in terrestrial environments. Spacecraft and satellites equipped with magnetometers and plasma wave instruments can detect these oscillations, capturing data on frequency, amplitude, and propagation direction, which scientists can then sonify to study temporal patterns, pitch, and intensity, in ways analogous to listening to musical tones, making the invisible structure and dynamics of space perceivable. Jupiter's magnetosphere, for instance, is so powerful and extended that it produces intense radio emissions and plasma oscillations, sometimes described as singing, due to the periodicity and tonal characteristics of the waves, and these emissions can be mapped to pitch and frequency ranges perceivable by humans when sonified, providing an acoustic representation of cosmic electromagnetic processes. Saturn II exhibits similar plasma wave activity, often associated with auroral emissions, magnetic reconnection events, and interactions with moons, demonstrating that magnetospheres act as natural laboratories for oscillatory phenomena that mimic the properties of sound in a mechanical medium. These plasma waves can interact with each other, producing resonance, interference, and reflection effects akin to echoes and standing waves, highlighting the universality of wave phenomena across different physical contexts, and offering insight into fundamental physics, including wave-particle interactions, energy dissipation, and the transport of momentum in a medium that is partially fluid and partially electromagnetic in character. Even the sun's corona and solar wind generate MHD waves, which carry energy outward, influencing G-planetary magnetospheres and sometimes causing geomagnetic storms on Earth, providing an indirect voice of solar activity that can be interpreted and monitored using instruments designed to capture these oscillations. The study of magnetospheric and plasma waves is not only academic, but practical, because understanding these oscillations helps predict space weather, protect satellites and astronauts from radiation hazards, and inform communication systems that may be disrupted by high-energy particle interactions. Conceptually, magnetospheric waves illustrate that the definition of sound is broader than simple mechanical propagation through air. Energy can travel via collective oscillations of charged particles, creating patterns and frequencies that can be interpreted as analogous to sound, reinforcing the idea that the universe is rich with vibrations, even in what humans would perceive as a vacuum. Sonification of these waves, converting electromagnetic or plasma oscillations into audible audio, has become a powerful tool for education and public outreach, allowing people to listen to the activity of planets and stars, connecting abstract physical processes to human perception and aesthetic experience, much as one might listen to music or natural sounds on Earth. Ultimately, magnetospheres demonstrate that, while space lacks traditional sound propagation, it is not devoid of wave phenomena. The interactions of plasma-charged particles and magnetic fields create oscillatory behaviors that convey energy and information across immense distances, and when translated into frequencies accessible to human ears, these cosmic processes reveal a hidden dynamic symphony that challenges our notions of silence, showing that the universe is never truly still, but constantly vibrating in ways that transcend the limitations of ordinary mechanical sound. Although space cannot carry sound in the conventional sense, it is a rich environment for electromagnetic waves, including radio waves, which, when converted into audio signals, provide an indirect way for humans to hear the universe, effectively turning the vacuum into a medium for perceivable information. These waves are generated by a wide range of astrophysical phenomena, from pulsars rapidly rotating neutron stars emitting beams of radiation at precise intervals, to active galactic nuclei, supernova remnants, and solar flares, each producing characteristic frequencies that, when captured by antennas and processed electronically, can be mapped into audible ranges, revealing patterns that resemble musical tones, pulses, or complex rhythmic sequences. Radio telescopes like the Arecibo Observatory, before its collapse, or the Very Large Array detect these waves across the spectrum, isolating narrow bands of frequency, amplifying faint signals, and digitizing them to allow sonification, a process that turns the temporal structure of cosmic radio emissions into sound we can perceive. For example, pulsars generate extremely regular pulses, some occurring hundreds of times per second, which, when shifted into human auditory range, produce a rhythmic clicking or ticking, giving the impression that space itself has a heartbeat and allowing researchers to measure rotation rates, magnetic fields, and distances with remarkable precision. Similarly, the Sun emits bursts of radio waves associated with solar flares and coronal mass ejections, which, when converted to audio, produce fluctuating tones or whistles, offering a sonic signature of solar activity and allowing scientists to study magnetic reconnection, particle acceleration, and plasma dynamics in ways that complement visual and X-ray observations. Radio waves from Jupiter, produced by interactions between its magnetic field and the Moon Io, create characteristic hissing, whistling, and roaring sounds when sonified, revealing the energetic interactions within the planet's magnosphere and highlighting the coupling between plasma motion and electromagnetic emission. Beyond our solar system, distant pulsars, quasars, and fast radio bursts contribute a complex background of cosmic noise, much of it imperceptible without technology. Amplification, but when shifted into audible frequencies, these signals form intricate soundscapes that can be analyzed for periodicity, intensity variation, and transient phenomena, helping astronomers detect new objects and understand extreme astrophysical processes. Sonification of radio waves also provides educational and artistic opportunities, translating otherwise abstract signals into sensory experiences that convey rhythm, intensity, and frequency variation in ways the human brain can intuitively grasp, effectively giving voice to the universe in a medium-free environment. These audio representations are not true sound in space but are powerful analogs, capturing the temporal and frequency structure of waves and mapping them onto parameters we can perceive with hearing, allowing the universe to communicate in a form that bridges physics, cognition, and emotion. The ability to hear cosmic radio waves has inspired musicians, sound artists, and educators to incorporate them into compositions, demonstrating that even though space is a vacuum, it can produce a rich tapestry of vibrational information, once translated through technology. This approach also aids scientific discovery because subtle changes in pulse timing, frequency drift, or amplitude modulation become more apparent when interpreted audibly, allowing patterns and anomalies to emerge that might be difficult to detect visually. Furthermore, cosmic radio waves highlight the universality of wave phenomena, showing that energy and information can travel across the vast emptiness of space without a traditional medium, and that perception is a matter of converting these waves into a form compatible with human senses. Ultimately, cosmic radio waves serve as the universe's audible signals, a bridge between silence and perception, demonstrating that while mechanical sound requires matter, the principles of oscillation, periodicity, and information transfer persist in space, and that with ingenuity, humans can access these hidden symphonies, transforming raw electromagnetic data into an experience that resonates with both scientific understanding and aesthetic appreciation. Echolocation, a biological sonar used by bats, dolphins, and other animals on Earth, illustrates a principle of sound that depends entirely on the reflection of waves from surfaces. And while mechanical sound cannot propagate through the vacuum of space, the concept of echo-based detection extends to extraterrestrial and technological environments, revealing the universality of wave-based perception. On Earth, animals emit sound pulses that travel through air or water, bounce off objects, and return as echoes, allowing them to map their surroundings, detect prey, or avoid obstacles with remarkable precision. And the timing, intensity, and frequency of these returning waves encode detailed spatial information, which is interpreted by highly specialized auditory systems. In the context of space exploration, spacecraft and rovers employ analogous techniques using radar, LiDAR, or sonar systems, sending electromagnetic or acoustic pulses that reflect off surfaces such as planetary terrain, ice layers, or asteroid regolith, effectively performing echolocation. Through media capable of carrying waves, translating the principles of sound-based perception into environments where conventional mechanical waves cannot propagate. For instance, NASA's planetary rovers, like those on Mars, use radar to probe subsurface ice deposits and map terrain, sending pulses that return after encountering different layers, much like a bat detecting obstacles in the dark. And these echoes provide scientists with detailed structural information, critical for understanding planetary geology and selecting safe landing or exploration sites. Similarly, space probes use sonar in the thick atmospheres of moons such as Titan, where methane-rich air or liquid layers can transmit mechanical vibrations, allowing the measurement of topography and fluid depth, essentially adapting biological principles of echolocation to non-Earth environments, demonstrating that the concept transcends the terrestrial limitations of sound. On a larger scale, radar astronomy employs high-frequency radio waves to illuminate asteroids, comets, and planetary surfaces, measuring the timing and intensity of return signals to calculate distance, shape, rotation, and composition, functioning as a form of echo detection at interplanetary distances and revealing that the fundamental physics of waves, emission, reflection, and detection remains applicable even in the absence of air. These technologies also exploit frequency shifts, analogous to the Doppler effect in echolocation, where motion of the reflecting body alters the frequency of the returned wave, allowing velocity measurement in addition to spatial mapping, which is vital for navigation and trajectory correction in deep space missions. Beyond practical applications, understanding how echoes work in different media illuminates fundamental acoustic principles, such as wave reflection, refraction, attenuation, and resonance, and highlights the constraints imposed by medium density, particle interaction, and frequency on effective signal detection. The design of echo-based instruments for extraterrestrial exploration must account for medium properties, temperature, pressure, and electromagnetic interference, optimizing pulse duration, frequency, and emission power to achieve reliable detection, much as animals' auditory systems have evolved to suit specific ecological niches. In environments like the vacuum of space, electromagnetic waves take the place of mechanical sound in transmitting information. Yet the logic of send a wave, detect its return, interpret the delay and distortion, mirrors the biological strategy of echolocation, demonstrating the universality of this approach across both natural and engineered systems. Echolocation-inspired technology also provides insight into mapping inaccessible or hazardous environments on Earth, such as deep oceans, caves, or glacial ice, reinforcing the broader applicability of sound-based detection principles and the power of wave reflection as a tool for spatial understanding. Moreover, studying the limits and adaptations of echolocation informs the development of autonomous navigation systems, where drones, rovers, and spacecraft rely on wave-based feedback to traverse complex environments without direct human control. Conceptually, the principle underscores a key truth. Sound is not merely a perceptual phenomenon, but a method of probing space and material, and even when the medium changes from air to water to plasma or vacuum with electromagnetic waves, the fundamental strategy of emitting energy and analyzing returning signals remains profoundly effective. Ultimately, the science of echolocation beyond Earth demonstrates that the echo is more than a biological curiosity. It is a universal method for acquiring information about an environment through wave propagation and reflection, adaptable across diverse media and distances, bridging biology, technology, and cosmic exploration, and revealing that even in the silence of space, echoes can exist in transformed, mediated forms, providing the tools for navigation, discovery, and understanding across worlds. Black holes, the most extreme gravitational objects in the universe, epitomize the concept of cosmic silence because, despite their enormous mass and energetic surroundings, they emit no sound in the conventional sense. These regions of space-time are defined by an event horizon, a boundary beyond which nothing, not even light or mechanical waves, can escape. And the medium outside a black hole is a near vacuum, incapable of supporting sound, meaning that the cataclysmic gravitational forces at play produce no audible waves for a human ear or even a conventional microphone to detect. However, The regions surrounding black holes are often sites of intense energetic phenomena, including accretion disks, relativistic jets, and magnetic turbulence, where plasma and ionized gas swirl at immense velocities, generating pressure waves and oscillations within the material itself, which can sometimes propagate as X-ray, radio, or gravitational waves. For instance, the accretion disk around a supermassive black hole can emit quasi-periodic oscillations detectable by space telescopes, which, when sonified, allow scientists to hear patterns that reflect the dynamics of matter spiraling into the abyss, providing insight into mass, spin, and the inner structure of the disk. Gradual lives from merging black holes also carry information about these objects' properties, producing characteristic chirps when interpreted through detectors like LIGO and Virgo, allowing humans to perceive these silent cosmic collisions as sound analogs, even though no mechanical vibrations propagate in the vacuum. The extreme gravity near a black hole affects spacetime itself, stretching and compressing it in ways that profoundly influence nearby matter and radiation, creating oscillations that can propagate through gravitational fields rather than through a physical medium, illustrating that the sound associated with black holes is a metaphorical and technological construct rather than a natural acoustic phenomenon. Observations of black hole mergers, supermassive black holes in galactic centers, and tidal disruption events where stars are shredded by gravitational forces all reveal that while the environment is violently dynamic, it remains acoustically silent in a vacuum, with all signals traveling via electromagnetic radiation, particle emissions, or spacetime distortions. Studies of these environments rely on translating physical signals into perceptible data, where fluctuations in X-ray intensity, radio emissions, or gravitational waveforms are mapped into audio frequencies, producing haunting representations that convey the rhythm, power, and timing of events occurring billions of kilometers away, effectively allowing humans to hear what nature cannot transmit mechanically. Even in the dense plasma surrounding black holes, where pressure waves exist, the extreme conditions, near light velocities, strong magnetic fields, and relativistic effects produce oscillations outside human auditory perception, requiring instrumentation and data processing to translate patterns into a perceptible form. Black holes thus exemplify the intersection between silence and energy. The most violent, massive, and dynamic objects in the universe produce no sound for unaided human perception, yet they generate measurable, interpretable signals across multiple physical channels, reminding us that auditory silence does not imply inactivity. In essence, black holes reveal that sound is a local, medium-dependent phenomenon, while energy, motion, and information continue to propagate through other mechanisms, including light, particles, and space-time distortions. By converting these signals into audible forms, scientists can study the hidden music of black holes, creating a bridge between the imperceptible cosmic processes and human sensory experience. Ultimately, black holes underscore the profound distinction between human perceived sound and universal vibration. Space may be silent to the ear, but it is filled with energy, oscillations, and dynamic interactions that, when mediated through technology, can be interpreted as a form of sound, revealing the hidden symphony of the cosmos, even in regions where nothing escapes the pull of gravity. Though the vacuum of space is often described as silent, the interstellar medium is the sparse gas, dust, and plasma filling the space between stars, supports a variety of wave phenomena that, while imperceptible to human ears, behave analogously to sound in a medium, allowing energy density fluctuations and magnetic interactions to propagate across vast distances. Composed primarily of hydrogen and helium, with traces of heavier elements and cosmic dust, the ISM is extremely tenuous, often containing only a few particles per cubic centimeter, yet these particles interact collectively through pressure, gravity, and magnetic fields, producing compressional and transverse waves that transport energy, influence star formation, and mediate turbulence across molecular clouds. Acoustic-like waves in the ISM, sometimes called magnetosonic waves, result from coupling between the gas pressure and magnetic field tension, creating oscillations that can compress or rarefy plasma regions, guiding the collapse of clouds into stars or dispersing energy from supernova shocks, highlighting that even in low-density environments, wave propagation plays a critical role in cosmic state rupture formation. These waves operate at frequencies far below human hearing, spanning periods from years to centuries, but through sonification and mathematical modeling, scientists can translate their temporal and spatial patterns into audible forms, revealing rhythmic structures that inform our understanding of turbulence, energy transport, and the life cycle of interstellar material. Shock waves from supernovae also propagate through the ISM, compressing gas and triggering star formation while carrying kinetic energy over thousands of light years, demonstrating that silence in space does not equate to the absence of mechanical phenomena, and that wave-based interactions underpin the evolution of galaxies and stellar systems. Radio telescopes detect fluctuations in density and magnetic fields in the ISM, which can be converted into sound for analysis, enabling the study of pulsar dispersion, cosmic ray propagation, and interstellar turbulence, essentially turning the faint whispers of gas and plasma into a perceivable auditory map of the galaxy. These waves are also crucial for understanding how matter and energy distribute within galaxies, affecting star formation rates, chemical enrichment, and the shaping of spiral arms as the ISM mediates interactions between stars, supernova remnants, and planetary systems. The physics of wave propagation in the ISM is governed by magnetohydrodynamics, combining fluid dynamics and electromagnetic fields interact to produce compressions, rarefactions, and resonances that distribute energy over enormous scales, illustrating that waves do not require Earth-like density to exert influence, only the ability for particles to respond collectively to forces Even the cosmic microwave background carries subtle anisotropies, fluctuations that can be considered relic acoustic oscillations from the early universe, encoded as density variations in the primordial plasma, which, billions of years later, inform cosmologists about the geometry, expansion, and evolution of the universe, and when mapped to sound, produce a haunting representation of the echoes of the Big Bang. Interstellar dust also interacts with waves in the ISM, affecting scattering, absorption, and polarization of electromagnetic signals, which indirectly provides information about the medium's acoustic-like behavior and its influence on the transmission of energy and information across galaxies. Ultimately, the interstellar medium exemplifies a universe where sound-like phenomena exist not for human hearing but as essential mechanisms of energy transfer, structure formation, and cosmic evolution, showing that the physics of oscillations, waves, and resonance is universal, and that even in the vast emptiness between stars, the universe vibrates in patterns that can be decoded, measured, and transformed into forms we can perceive, offering an audible window into processes that shape galaxies, stars, and planets. The Sun, far from being a silent ball of plasma, constantly vibrates in complex patterns known as solar oscillations, producing pressure waves called P-modes that travel through its interior and ripple across its surface, a phenomenon studied in the field of helioseismology, which allows scientists to probe the Sun's internal structure, rotation, and dynamic behavior in ways impossible through direct observation alone. These oscillations are caused by the interplay of gravity, pressure, and convection within the solar plasma, generating compressional waves that move in all directions, reflecting off boundaries within the Sun and interacting with other waves to produce interference patterns, standing waves, and resonances, effectively turning the Sun into a gigantic, self-resonating sphere whose vibrations encode information about its density, temperature, and chemical composition. Although these oscillations occur at frequencies far below the threshold of human hearing, specialized instruments, like the Michelson Doppler imager, on the SOHO and ground-based networks, such as the Global Oscillation Network Group, GON-based networks such as the Global Oscillation Network Group, allowing scientists to reconstruct these waves and even convert them into audible sound through sonification, producing haunting low-frequency tones that provide insight into the sun's interior. The study of solar oscillations has revealed critical information about the differential rotation of the sun, the depth of its convection zone, and the properties of its core, enabling tests of stellar models and comparisons with other stars, illustrating that sound-like vibrations, even when inaudible, carry a wealth of scientific information. These oscillations also influence solar phenomena, including sunspots, flares, and magnetic activity, as resonant waves interact with the sun's magnetic field, producing localized amplification or damping of motion, affecting energy transport, and modulating the solar atmosphere in ways that can impact space weather, planetary magnetospheres, and even conditions on Earth. P modes are complemented by G modes, gravity-driven oscillations that penetrate deeper into the radiative zone, offering a glimpse into the core structure, while F modes, or surface gravity waves, propagate along the sun's exterior, demonstrating a spectrum of oscillatory behavior that mirrors terrestrial acoustic phenomena on vastly larger scales. The sun's oscillations also serve as a natural laboratory for studying wave physics in high-temperature plasma, including mode coupling, damping mechanisms, nonlinear interactions, and energy propagation, highlighting universal principles that apply to both stellar and terrestrial acoustics, albeit in radically different conditions. Beyond pure science, translating these oscillations into sound allows humans to listen to sound, allows humans to listen to the sun, providing an experiential connection to the otherwise invisible dynamics of our closest star, reinforcing the concept that silence in space is often a matter of perception rather than absence of activity. The sun's hidden symphony is not static. Waves continually change in response to evolving magnetic fields, convective flows, and solar cycles, creating a dynamic and ever-changing soundscape of frequencies and amplitudes, much like a cosmic orchestra playing variations across decades, centuries, and millennia. This auditory analogy helps scientists intuitively grasp complex interactions, detect subtle anomalies, and communicate findings to the public, making the sun's activity comprehensible in both scientific and aesthetic terms. Ultimately, solar oscillations demonstrate that even in seemingly silent celestial objects, mechanical vibrations exist at scales and energies far beyond human experience, and when mediated through technology, these waves reveal a universe in motion, rich in structure, rhythm, and resonant patterns, providing both knowledge and a profound sense of connection to the hidden music of the cosmos. Planetary atmospheres offer unique environments in which sound can exist beyond Earth, though the properties of sound, speed, frequency, attenuation, and timbre depend entirely on the composition, density, temperature, and pressure of the atmospheric medium, creating acoustic conditions vastly different from terrestrial experience. For instance, Venus, with its thick carbon dioxide atmosphere and surface pressures about 92 times that of Earth, allows sound to propagate much faster and with higher attenuation, meaning that explosions, wind, or mechanical vibrations would sound deeper, louder, and more resonant than on Earth, while Mars, with a tenuous carbon dioxide atmosphere about 1% as dense as Earth's, drastically reduces sound transmission, producing faint, high-pitched, and quickly dissipating sounds that challenge traditional recording equipment. Researchers have used landers and rovers to measure and interpret sound propagation on these planets, such as NASA's Perseverance rover, which includes microphones capable of recording Martian wind, dust interactions, and even mechanical operations, demonstrating that even thin atmospheres support acoustic phenomena, though at altered frequencies and amplitudes, offering insight into planetary weather, surface processes, and environmental conditions. The study of sound on other planets informs both scientific understanding and technological design, influencing the development of communication systems, exploration tools, and SAR detection mechanisms. Because the effectiveness of sound-based sensors depends on atmospheric density, temperature, and composition, which control wave speed, reflection, and absorption. On Titan, Saturn's largest moon, the dense nitrogen-rich atmosphere and presence of methane lakes create conditions where sound travels slower than on Earth but over longer distances with less attenuation, allowing unique acoustic behaviors for hypothetical exploration vehicles or probes, and potentially supporting phenomena such as echoes, resonance, and interference patterns that differ dramatically from terrestrial norms. Sound in planetary atmospheres is also influenced by wind, turbulence, and thermal gradients, which can bend, scatter, or refract waves, producing effects analogous to mirages in optics, including frequency shifts, distortion, or localized amplification, challenging researchers to account for these factors when designing instruments or interpreting recordings. Even within our own solar system, auroral activity, lightning, and meteor impacts generate acoustic waves that can be measured in atmospheres with sufficient density, providing a method to study weather patterns, storm intensity, and electrical phenomena remotely, effectively translating planetary vibrations into detectable signals for analysis. The physics underlying these sounds remains the same as on Earth. Pressure waves compress and expand the local medium, transferring energy through molecular collisions, but the unique environmental parameters, composition, pressure, temperature, and gravity, alter the speed of sound, its frequency response, and its damping, producing effects that are both scientifically informative and experientially alien. Understanding these acoustic characteristics is crucial for interpreting recordings, predicting environmental hazards, and designing instruments that can function reliably. Because low-density atmospheres like Mars's significantly weaken sound signals, whereas dense atmospheres like Venus's amplify and lower frequency ranges, illustrating the diversity of acoustic environments in our solar system. Sonofika techniques can also be applied, converting subtle pressure oscillations, wind interactions, or dust impacts into audible sound for human perception, effectively creating a bridge between the alien acoustic environment and human sensory experience, providing both scientific insight and educational value. These studies reveal that while the cosmos is silent in vacuum, wherever a medium exists, no matter how thin or dense, sound can propagate, offering unique opportunities to study planetary physics, atmospheric dynamics, and environmental conditions through acoustic measurements. Ultimately, planetary atmospheres demonstrate that sound is a universal consequence of matter and motion, that each world shapes its own auditory landscape, and that by understanding and recording these signals, humans can listen to alien worlds, expanding our sensory connection to the solar system and providing a complementary perspective to light-based observations, revealing dynamics, events, and phenomena that might otherwise remain hidden in silence. Comets and asteroids, often portrayed as silent travelers of the solar system, possess subtle acoustic behaviors when considered within the context of their material composition and interaction with surrounding gas or dust, revealing that even small, airless bodies can generate mechanical vibrations, though these sounds cannot propagate through the vacuum of space without a medium. When a comet approaches the sun, solar heating causes sublimation of ices, releasing gas and dust and jets that exert pressure on the comet's surface, creating vibrations within its structure. These microseismic events resemble low-frequency sounds, traveling through the cometary nucleus itself, which can be detected by instruments if a lander or probe is in contact with the surface, as in the case of ESA's Rosetta, whose lander Philae recorded mechanical responses from sublimation processes and mechanical impacts, offering insight into internal composition, density, and structure. Similarly, asteroids experience, and so, impacts from micrometeoroids and collisions with other small bodies producing seismic waves that propagate through their interiors. These vibrations, though inaudible externally due to vacuum, inform scientists about internal cohesion, layering, and porosity, allowing a form of asteroid seismology. that parallels terrestrial techniques used in earthquake studies. Laboratory simulations on Earth, including impact experiments and vibration modeling, help researchers understand how energy from collisions propagates through small bodies, influencing surface morphology, regolith movement, and crater formation, while also revealing the damping effects of low gravity and loosely bound material. Thermal stresses caused by rapid heating and cooling as comets rotate create fracturing and cracking in the surface ice, producing additional microvibrations that carry information about mechanical properties and structural weaknesses, which can be captured by sensitive seismometers or inferred from changes in trajectory or dust emissions. These internal vibrations also affect dust and gas release, subtly modulating the activity of cometary jets and producing oscillatory patterns in emitted material, which can be detected remotely through imaging, spectroscopy, or radio observations, and then interpreted as evidence of internal acoustic processes. Modeling these vibrations enhances understanding of small body dynamics, stability, and evolution, which is crucial for assessing potential threats from near-Earth objects, designing mitigation strategies, and planning landing or sampling missions that rely on interaction with the surface without destabilizing the body. Even in the absence of air, researchers can listen to comets and asteroids by converting vibration data, dust impact timing, or gas emission oscillations into audio signals, creating a form of sonification that translates otherwise imperceptible mechanical phenomena into a form accessible to human perception, aiding both analysis and public outreach. Tidal interactions, particularly with comets or asteroids passing near planets, can induce additional vibrations and stress waves within these bodies, further demonstrating that mechanical activity exists even in ostensibly silent, airless environments. Fundamentally, the study of acoustic activity in comets and asteroids reinforces the principle that sound is not an absolute requirement for vibration and energy transfer. Mechanical waves exist wherever matter can transmit them, and by observing or measuring these waves locally, humans can interpret processes that would otherwise be completely invisible. These investigations also reveal the interplay between internal structure, composition, and external forces, highlighting how small bodies respond to stress, heat, and impacts, and how subtle vibrations contribute to long-term evolution, fragmentation, or surface modification. Ultimately, comets and asteroids illustrate that while space is silent in the vacuum, the bodies within it are often singing through internal vibrations, impacts, and sublimation-driven oscillations, which, when measured and interpreted with technology, provide a hidden symphony of information about the formation, composition, and dynamics of these primordial remnants of solar system evolution. Aurors, the spectacular light displays observed near planetary poles, provide a striking example of how wave phenomena in space can produce sound-like effects, even though mechanical sound cannot propagate through the near vacuum of the upper atmosphere and magnetosphere. Auroras are caused by charged particles, primarily electrons, streaming along magnetic field lines from the solar wind, colliding with atoms and molecules in the upper atmosphere, which excites them and produces visible light, while simultaneously generating plasma waves, electromagnetic oscillations, and field-aligned currents that propagate through ionized gas, effectively creating vibrations analogous to sound waves in a medium. On Earth, these plasma waves can interact with magnetic field lines to produce extremely low frequency, LF, and very low frequency, VLF, and very low frequency, which, though inaudible to the human ear in their natural form, can be captured by radio receivers or magnetometers and then converted into audible sound through sonification, producing hissing, crackling, and pulsating tones that correlate with auroral activity. Similar processes occur on Jupiter and Saturn, where intense magnetospheres and strong plasma interactions generate powerful radio emissions, often referred to as aurora, which, when translated to audio frequencies, produce dramatic sounds that reveal the dynamics of charged particle interactions and magnetic field oscillations. effectively giving the universe a voice through electromagnetic mediation. These auroral waves are important not just for aesthetic reasons, but for understanding energy transfer from the solar wind into planetary magnetospheres, particle acceleration, and the coupling between magnetic fields and plasma, as the oscillations carry information about field strength, density, and particle flux that cannot be obtained through optical observation alone. Scientists also use these plasma wave recordings to study space weather, including geomagnetic storms and substorms, which can disrupt satellite operations, radio communications, and power grids, demonstrating that auroral sound provides both scientific insight and practical benefits for technological systems on and around Earth. Laboratory cyst emulations of auroral plasma waves further reveal how charged particles excite oscillatory modes in a magnetized medium, producing wave-particle interactions, resonance, and damping analogous to acoustic phenomena, which can be modeled and scaled to understand planetary environments throughout the solar system. These studies show that waves do not require a dense atmosphere to convey energy and information. Charged particles and electromagnetic fields form a medium capable of transmitting vibrations that, while not audible directly, reflect dynamics comparable to sound in a terrestrial medium. For humans, the sonification of auroral waves provides a unique sensory bridge to an otherwise imperceptible process, allowing both scientists and the public to perceive the timing, intensity, and variability of plasma activity, transforming abstract space physics into a tangible auditory experience. Auroral acoustic analogs also illustrate fundamental physics principles, such as wave propagation, resonance frequency modulation, and interference, highlighting that the universe operates under the same wave-based laws that govern sound even in environments where traditional air-based propagation is impossible. Moreover, these electromagnetic sounds convey temporal patterns, including periodic pulsations, linked to solar wind fluctuations, rotational modulation, and magnetospheric instabilities, giving insight into how planetary magnetic environments respond dynamically to external stimuli. Ultimately, auroras demonstrate that while mechanical sound cannot exist in the upper atmosphere or magnetosphere wave phenomena, plasma oscillations, electromagnetic pulses, and field-aligned currents produce vibrational signatures that can be interpreted as a form of cosmic sound, revealing that even in the apparent silence of space, energy moves, interacts, and resonates, allowing humans, through technology and sonification, to listen to the dynamic interplay of particles, fields, and waves that create the mesmerizing auroral spectacle. Solar flares, among the most energetic events in the solar system, illustrate a dramatic example of how the universe can release vast amounts of energy in near-complete silence. Since the vacuum of space cannot transmit mechanical sound, yet the physics of wave propagation, particle acceleration, and electromagnetic radiation allows humans to perceive these events through indirect means. A solar flare occurs when magnetic energy stored in the sun's atmosphere is suddenly released, accelerating charged particles and emitting intense bursts of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays, producing effects that can impact planetary atmospheres, magnetospheres, and technological systems, but without generating audible sound waves beyond the sun's surface. These flares produce shock waves in the solar corona and surrounding plasma, which propagate as compressional and magnetohydrodynamic (MHDT) waves, creating oscillations in the sun's atmosphere that can be detected remotely by satellites, spectrometers, and radio instruments, allowing scientists to reconstruct the event, measure energy release, and understand particle acceleration mechanisms. Sonification of solar flare data enables the translation of these oscillations, particle fluxes, and electromagnetic variations into audible sound, producing crackling, hissing, or pulsing tones that convey the timing, intensity, and dynamics of the flare, providing a perceptual bridge between human senses and the otherwise silent energy release. Beyond their acoustic analogs, solar flares can trigger geomagnetic storms on Earth, producing induced currents in power grids, auroras, and radio communication disruptions, illustrating that although the sun's explosive events do not transmit sound through space, their energetic effects have tangible consequences, detectable and interpretable on planets with atmospheres and magnetospheres. Studying the oscillatory behavior associated with flares also illuminates wave-particle interactions, resonance phenomena, and energy dissipation in magnetized plasma, revealing how energy is transported, and redistributed in stellar environments. The rapid rise and gradual decay of flare emissions, combined with oscillatory substructures, can be mapped into time-varying audio signals, allowing scientists to perceive patterns, periodicities, and anomalies that inform models of solar magnetic reconnection, coronal heating, and flare frequency. Even the most massive flares, which release energy equivalent to millions of nuclear bombs in minutes, produce no audible sound in the vacuum between sun and planets, highlighting the fundamental principle that mechanical sound requires a medium, and that energetic events in space communicate through electromagnetic, particle, and gravitational channels rather than pressure waves. Flare-related plasma waves also propagate along magnetic field lines, creating standing waves, reflections, and interference patterns within the corona, which, while imperceptible to the unaided ear, can be modeled and sonified to provide a sense of rhythm and structure, akin to an otherworldly symphony. Understanding these processes is essential for space weather prediction, protection of satellites and astronauts, and interpretation of solar activity over time, linking acoustic analogs with practical and scientific applications. Ultimately, solar flares exemplify the universe's ability to generate extreme energy releases that are acoustically silent, yet rich with vibrational, electromagnetic, and particle-based phenomena, demonstrating that sound is only one way of perceiving energy, and that the cosmos contains layers of oscillation, resonance, and dynamic behavior that can be translated into perceptible forms through technology, allowing humans to listen to the hidden music of stellar explosions and gain insight into the fundamental physics governing our sun and other stars. Neutron stars, the ultra-dense remnants of massive stellar explosions, offer a fascinating example of cosmic objects that produce precise, rhythmic oscillations, which, while inaudible in the vacuum of space, can be translated into sound through technology, revealing an extraordinary form of cosmic music, detectable by humans. These stars, with masses comparable to the Sun, compressed into a sphere only about 20 kilometers across, rotate at incredible speeds, sometimes hundreds of times per second, emitting beams of electromagnetic radiation from their magnetic poles. And when these beams sweep past Earth, they are observed as regular pulses, hence the name pulsars. The pulsed emissions from neutron stars span radio, optical, X-ray, and gamma-ray frequencies, with timing so precise that pulsars rival atomic clocks in stability, allowing astronomers to measure rotation, gravitational effects, and even detect orbiting companions through slight variations in pulse timing. Although no mechanical sound propagates from the star itself, scientists can convert the pulse frequency into audible ranges, producing steady, rhythmic clicks, beats, or tones, giving humans a sense of the periodicity and structure of these extreme objects and providing an intuitive grasp of phenomena otherwise entirely abstract. The physics behind pulsar emissions involves rotation, intense magnetic fields, relativistic particle acceleration, and plasma interactions, generating coherent radiation through processes such as curvature radiation or synchrotron emission, which propagate through space unimpeded, carrying detailed information about the star's interior structure, spin rate, and environment. Neutron star oscillations can also include quasi-periodic oscillations and starquakes, where sudden structural adjustments produce vibrations within the crust, analogous to seismic waves, which, although unhearable externally, encode information about the neutron star's composition, rigidity, and equation of state. By studying these oscillations and translating them into sound, scientists can gain insight into the physics of matter at nuclear densities, test models of extreme gravity, and explore phenomena inaccessible on Earth, effectively giving the universe a rhythmic voice through the lens of electromagnetic detection and sonification. Pulsars also serve as natural labor, areas for testing general relativity, detecting gravitational waves indirectly, and probing the interstellar medium, as pulse timing variations reveal dispersion, scattering, and magnetic field effects along the line of sight, which can be analyzed through audio representations for pattern recognition and intuitive understanding. Beyond scientific analysis, the audible representation of pulsars has inspired educational tools, public outreach, and artistic interpretation, allowing people to listen to the heartbeat of the cosmos, experiencing the precision, regularity, and occasional irregularities of objects born in violent supernovae. Moreover, pulsar sound analogs emphasize the broader principle that wave phenomena are universal, and while mechanical sound requires a medium, electromagnetic pulses and oscillations carry structured information across the vacuum of space, capable of being perceived once converted into human-compatible forms. The study and sonification of pulsars not only provide a tangible connection to distant stellar remnants, but also illustrate the incredible variety of vibrational behavior in the universe, from silent nuclear density cores to the rhythmic signals detectable across thousands of light years. Ultimately, neutron stars demonstrate that the cosmos is full of patterned oscillations, timing signatures, and wave-based communication, and with appropriate technology, humans can interpret and experience these silent signals as sound, bridging the gap between the imperceptible vacuum and our sensory world, and transforming abstract astrophysics into perceivable, rhythmic, and profoundly evocative auditory experiences. Exoplanets, planets orbiting stars beyond our solar system, offer an entirely new realm for exploring sound, or more precisely, the propagation of waves within alien atmospheres, where variations in atmospheric composition, pressure, temperature, and density create acoustic environments dramatically different from Earth, shaping the potential soundscape of these distant worlds. While mechanical sound cannot travel through the vacuum of space, within an exoplanet's atmosphere, pressure waves can propagate according to the local properties of the medium, meaning that storms, winds, volcanic activity, or surface interactions could produce sound, albeit at frequencies, amplitudes, and speeds that depend on the chemical makeup and density of the atmosphere. For instance, a dense hydrogen-helium atmosphere on a gas giant might transmit sound faster and with lower attenuation than an Earth-like nitrogen-oxygen mix, producing deeper tones and richer resonance, whereas a thin carbon dioxide or methane atmosphere might weaken or distort sound waves, resulting in faint, high-pitched, or quickly dissipating acoustic phenomena. Studying these conditions involves modeling atmospheric physics, including temperature gradients, molecular composition, and pressure profiles, which determine the speed of sound, absorption coefficients, and the frequencies that could propagate effectively, allowing scientists to predict how acoustic energy behaves in alien environments. Indirect methods, such as observing cloud movements, storm systems, or planetary weather through light and radio emissions, combined with atmospheric modeling, can provide estimates of turbulence and wave behavior, enabling researchers to simulate what sound might be like on these distant worlds, even if direct recording is impossible. In some cases, electromagnetic analogs of sound, such as radio emissions caused by charged particle interactions with magnetic fields, may provide information about atmospheric dynamics and turbulence, which can be translated into audible frequencies through sonification, offering a form of cosmic listening to alien weather systems. Extreme environments, such as superheated atmospheres on close-in exoplanets, strong winds exceeding thousands of kilometers per hour, or multi-layered clouds with varying densities, create opportunities for complex wave interactions, resonance, and interference. shaping acoustic phenomena in ways unimaginable on Earth and providing insight into atmospheric circulation, energy transport, and planetary evolution. Understanding potential acoustic properties of exoplanet atmospheres is not only scientifically fascinating, but also relevant for future exploration, communication, and interpretation of signals, since sound-like pressure waves affect atmospheric dynamics, shock propagation, and energy dissipation, which can influence habitability, climate modeling, and detection of surface or atmospheric events. Advanced simulations can even convert predicted acoustic vibrations into audible sonifications, allowing scientists and the public to hear storms, winds, and turbulence on exoplanets, bridging the gap between distant, unobservable phenomena and human perception. Studying sound in alien atmospheres also highlights the universality of wave physics. While the medium and parameters differ, the same fundamental principles of compression, rarefaction, resonance, and damping apply, demonstrating that sound-like behavior is a natural consequence of any medium, with particles capable of transmitting pressure waves. Ultimately, exoplanetary atmospheres expand our understanding of acoustic environments beyond Earth, showing that while space itself is silent, wherever a medium exists, waves propagate, energy moves, and phenomena analogous to sound can occur, offering the tantalizing possibility of alien soundscapes that challenge our intuition, broaden our sensory imagination, and allow humans to experience the universe not only visually, but also through a conceptual auditory lens. Supernovae, the catastrophic explosions marking the death of massive stars, generate some of the most energetic shock waves in the universe, propagating through the interstellar medium with incredible force, yet producing no conventional sound in space due to the near-vacuum conditions. These interstellar shocks compress gas and plasma, accelerate particles, and create turbulence across vast distances, carrying energy and momentum in ways analogous to the propagation of sound waves in a medium, but relying on particle interactions and magnetic fields rather than molecular collisions. As the shock wave expands, it generates density fluctuations and pressure gradients in the surrounding interstellar gas, producing magnet-to-hydrodynamic waves that can travel for hundreds or thousands of light years, structuring nebula, triggering star formation, and influencing the dynamics of galactic environments. Instruments such as radio telescopes, X-ray observatories, and spectrometers detect these disturbances through electromagnetic signatures, including emission lines, synchrotron radiation, and temporal variations, allowing scientists to reconstruct the propagation and energy of the shock, effectively listening to the explosion through indirect waveforms, rather thist, and mechanical sound. Sonification techniques can convert these data into audible forms, translating the timing, intensity, and frequency of fluctuations into sound that humans can perceive, creating a haunting audio representation of events that occur across millions of kilometers and decades of travel time. The physics of interstellar shocks involves nonlinear wave propagation, reflection, and damping in a medium of varying density, illustrating that wave phenomena and energy transport are universal, even in environments where traditional acoustic waves cannot exist. Interactions between multiple supernova remnants, stellar winds, and existing interstellar clouds can create interference patterns, resonances, and turbulence, producing complex oscillatory behavior that, if mapped into sound, resembles a dynamic, evolving symphony, conveying both the violence and rhythm of cosmic processes. These shock waves also accelerate cosmic rays, modify magnetic fields, and redistribute chemical elements, demonstrating that although the universe is silent to the ear, the information carried by waves and vibrations has profound consequences for galactic evolution, planetary formation, and the distribution of matter. By studying the echoes and oscillations within supernova remnants, astrophysicists gain insight into the density, structure, composition, and physical properties of the interstellar medium. Much like how geologists study seismic waves to understand Earth's interior, The interplay of expansion, compression, and particle acceleration produces temporal patterns that, when sonified, allow researchers to detect subtle variations, anomalies in periodicities, revealing the hidden dynamics of regions otherwise invisible. In addition, these shock waves influence the formation of molecular clouds and the ignition of new stars, demonstrating that even silent events can orchestrate the birth of cosmic structures, analogous to how sound can shape environments in fluid or elastic media on Earth. Ultimately, interstellar shocks exemplify how energy, motion, and information propagate through space without mechanical sound, showing that the universe communicates through waves, vibrations, and particle interactions, and that with careful observation, modeling, and translation into audible formats, humans can perceive and appreciate the rhythmic, dynamic, and dramatic symphony of the cosmos, capturing the silent roar of supernovae and their transformative impact on the galaxy. The cosmic microwave background, CMB, the faint afterglow of the Big Bang, represents a unique form of sound from the early universe consisting of primordial density fluctuations in a hot, dense plasma that existed approximately 380,000 years after the Big Bang, long before atoms formed, and the universe became transparent to light. In this primordial plasma, photons, electrons, and baryons were tightly coupled, creating pressure waves, known as acoustic oscillations, that propagated through the medium at relativistic speeds, compressing and rarefying regions of matter much like sound waves in air, effectively producing a cosmic symphony of density fluctuations across the early universe. These oscillations left an imprint on the CMB in the form of temperature anisotropies and polarization patterns, which today are observed by satellites like Planck and WMAP, allowing cosmologists to study the geometry, composition, and evolution of the universe with extraordinary precision. Although no mechanical sound has survived across 13.8 billion years of expansion and vacuum, scientists can translate these primordial oscillations into audible frequencies through sonification, effectively letting humans hear the echoes of the Big Bang, producing a haunting, low-frequency hum that represents the rhythmic compression and rarefaction of the early cosmic plasma. The physics underlying these primordial acoustic waves involves the interplay of gravity, photon pressure, baryonic matter, and dark matter, creating standing waves of varying wavelength, amplitude, and frequency, which later determined the size and distribution of galactic structures, clusters, and voids, illustrating that the universe's large-scale structure carries the legacy of early sound patterns. The CMB also encodes information about the rate of expansion, the proportion of ordinary matter, dark matter, and dark energy, as well as subtle features such as baryon acoustic oscillations, which continue to serve as cosmic rulers for measuring distances and understanding the evolution of cosmic expansion. Sonification of CMB data allows researchers to perceive the temporal and spatial patterns in a way that engages human intuition, highlighting peaks, troughs, and variations in the density waves, and providing a sensory experience of phenomena that are otherwise entirely abstract and invisible. These primordial acoustic oscillations illustrate that wave propagation is a fundamental process in nature, capable of leaving lasting imprints, even when the medium transitions from a dense plasma to a near-perfect vacuum, aiding the universality of wave-based energy transfer and resonance. Beyond scientific analysis, listening to the sonified CMB fosters a philosophical and aesthetic understanding of the universe, connecting human perception to the cosmic narrative, showing that even in silence, the universe retains memory of its earliest rhythms. Ultimately, the cosmic microwave background serves as the ultimate example of space's hidden soundscape, where vibrations of primordial matter created lasting structure, encoded information, and produced patterns that can be transformed into perceivable audio, allowing humanity to experience the echo of the Big Bang, bridging the gap between a silent vacuum and the rich vibrational history of the universe. Gamma-ray bursts, GRBs, are among the most energetic and luminous events in the universe, releasing in seconds more energy than the sun will emit over its entire 10 billion year lifetime. Yet they occur in the vacuum of space, where no mechanical sound can propagate, making them acoustically silent to human ears. These bursts are generated by cataclysmic phenomena, such as the collapse of massive stars into black holes, long GRBs, or the merger of neutron stars, short GRBs, which eject highly relativistic jets of particles and photons into space, producing intense gamma-ray radiation that travels across billions of light-years. Despite the absence of conventional sound, the physical processes associated with GRBs create shock waves, magnetohydrodynamic oscillations, and relativistic turbulence in the surrounding plasma, which can be detected through electromagnetic signals, gravitational waves, and high-energy particle emissions. Offering a way to study these extreme events indirectly, instruments like the Fermi Gamma Ray Space Telescope and Swift Observatory capture the intensity, timing, and spectral properties of GRBs, and sonification techniques can convert these data into audible forms, allowing humans to perceive the burst as a rapid series of clicks, pulses, or high-intensity tones, translating temporal variations in energy flux into a sensory experience. GRBs also produce afterglows across X-ray, optical, and radio frequencies, which carry information about the environment around the burst, including interstellar medium density, magnetic fields, and jet structure. And these oscillations can be mapped into sound to reveal underlying wave patterns and dynamics. The physics of GRBs involves relativistic beaming, particle acceleration, magnetic reconnection, and shock propagation, illustrating how energy can be transmitted through extreme processes without generating mechanical sound, while still producing measurable vibrations in electromagnetic fields and particle fluxes. Studying GRB data through sonification not only aids scientific understanding of stellar evolution, black hole formation, and extreme relativistic physics, but also allows humans to conceptually hear the scale, intensity, and timing of events that occur billions of light years away, providing both analytical and aesthetic insight into cosmic violence. Even though these explosions are silent in the vacuum, their impact on surrounding matter, potential generation of gravitational waves, and the structured nature of relativistic jets create oscillatory patterns that, when interpreted correctly, offer a form of rhythm and temporal structure analogous to sound. GRBs also inform broader cosmological studies, including star formation rates, galaxy evolution, and the distribution of matter in the early universe, highlighting that even silent events carry signatures of profound physical processes. Ultimately, gamma-ray bursts exemplify the paradox of cosmic silence. The universe can unleash unimaginable energy and dynamic motion without producing audible sound, yet through electromagnetic observation, data analysis, and sonification, humans can perceive, interpret, and even experience these events as a kind of cosmic sound, bridging the gap between physical phenomena and human sensory understanding, and demonstrating that silence in space is only a limitation of our ears, not of the waves, oscillations, and vibrations that permeate the cosmos, such as those encircling Saturn, are composed of countless particles of ice, rock, and dust, which interact through collisions, gravitational perturbations, and collective oscillations, creating mechanical vibrations within the rings that resemble sound waves, though these cannot propagate beyond the medium itself due to the vacuum surrounding them. The dynamics of ring particles produce density waves, bending waves, and spiral patterns that travel through the ring material, caused by gravitational resonances with moons, rotational shear, or self-gravity within dense ring regions, and these oscillatory motions can be measured by spacecraft as variations in particle density, speed, or spatial configuration. Instruments aboard missions such as Cassini captured subtle vibrations and wave propagation in Saturn's rings by monitoring the motion of ring edges, gaps, and embedded moons, providing indirect data that can be converted into sonified audio to reveal rhythmic structures, oscillation frequencies, and resonant interactions. Density waves in rings act like sound waves in a solid or fluid, with compressions and rarefactions traveling through He particle medium at velocities dependent on particle size, mass, spacing, and gravitational influences, producing a complex acoustic analog that maps the spatial and temporal behavior of the rings. Bending waves, excited by moons with inclined orbits, cause vertical oscillations in the ring plane, generating periodic motion that can interact with other waves to create interference, amplitude modulation, and damping effects, offering a rich, dynamic system for studying collective behavior. And resonances in granular media. The study of ring vibrations helps scientists understand the mass distribution, particle composition, and dynamic evolution of planetary rings, revealing how moons sculpt gaps, trigger waves, and induce resonant patterns, effectively turning ring systems into natural laboratories for wave physics, orbital mechanics, and granular dynamics. Sonifying these oscillations transforms otherwise imperceptible motion into audible patterns, allowing researchers and the public to experience the rhythm and structure of the rings, from slow undulating waves to rapid resonant oscillations, producing a sensory connection to these alien systems. Interactions among ring particles, including collisions, clumping, and scattering, contribute to energy dissipation, momentum transfer, and wave propagation, demonstrating that even in sparse, near-vacuum conditions, a medium-dense enough to allow local particle interactions can support complex vibrational phenomena. Planetary ring studies also inform understanding of protoplanetary disks, asteroid belts, and other circumstellar structures, highlighting universal principles of wave propagation, resonance, and collective motion across a variety of astrophysical systems. Ultimately, Saturn's rings and similar systems exemplify how sound-like vibrations can exist locally within particle media in space, creating hidden rhythms and patterns that reveal the history, dynamics, and ongoing evolution of these spectacular structures, allowing humans, through measurement and sonification, to perceive a subtle, silent music woven into the motions of countless tiny worlds.